Hi grade 12s, welcome to my channel. Let us have a look at the fundamental counting principle as well as questions relating to it. Anyway guys, this part of maths, or should I say this section of maths, paper 1, is not really too much on the theory part of it, but it's more on the doing. So it's all about the technique to solving problems here. And in essence, this is just a very convenient way of making counts, or should I say counting, that would be quite complex if we were to look at it manually. But there is some little bit of modeling that is useful here, which gives us a bit of the manual aspect of doing the calculations, and the rest becomes very easy. All right. So I do hope that as we walk through this document, you will probably get the hang of things and perhaps see where the little bit of modeling comes in and what it translates to in the larger scale. So it's quite a very nice topic. Yeah, this is where the problems come, especially this section. I personally do not claim to know everything in this topic. Sometimes I just get it all wrong. So yeah guys, this can be quite exhausting. So please take time to practice this and make sure the little bit of practice that you do, you carefully examine, analyze, and ensure that you understand at least what you can accomplish and what you can do. You never know when it's going to favor you in the exam. But yeah, this can be quite a disaster. Right, so folks, if we look at the fundamental counting principle, what is its purpose? Fundamental counting principle. Right. Now, I don't know if this fundamental is correct though. I think it's it's fundamental. I think it's A here. I'm not too sure guys, whatever. Yeah, simple, but whatever. I think it's fundamental. Anyway, folks, what is the utility of all of this? Because at the end of the day, it doesn't help to study things that we cannot put some sense into. So basically, the fundamental counting principle, it just helps us. I can say it helps determine the number the number of different ways to accomplish So this helps determine the number of different ways to accomplish different tasks. Okay, so what is key to this, guys, is to determine the number of different ways, not similar ways, but different ways to accomplish different tasks. Please, folks, please understand this and make sure you understand exactly what we are all about. So the fundamental counting principle helps us to determine a number or the number of different ways to accomplish different tasks. Now, we often state what a principle is all about, isn't it? Think of Newton's laws of motion. Those are principles. So what does this state? It states that if there are n ways of performing one task, and m ways of performing another task. There will therefore there will therefore be n times m number of ways to perform both tasks. Right. Maybe together or something. That is essentially the idea. So this principle states that if there are n ways of performing one task and m ways of performing another task, there will therefore be, or maybe let's just say therefore, the language, sometimes the English language is the thing, you see, is the thing. Okay, it states that if there are n ways of performing one task and m ways of performing another task, there will be n times m different ways of performing the tasks together. I'll probably say that, okay? But again, guys, revise the definitions. There's nothing as useless a student who does not know the definitions. That student is useless. Sorry to say it. Sorry to burst your bubble. If you cannot at least grasp the very definitions of any idea, topic, principle, whatever, if the definition is not in order, folks, that's already a recipe for disaster. Get that done, okay? So again, definitions or to define something is all cute, nice and dandy, but it's meaningless if its purpose is not clearly defined. Because what's the point of saying things or naming things or defining things if there's no purpose behind it? As you can see here, since this topic in particular, it's not really that theoretically based in a way. It's more of an action type of a thing, like a technique based, issue. Here, we're just going to be heavily relying on logic. Okay, so that is just the idea behind all of this. So this helps us to determine the number of different ways. Keyword is different ways. It's not about repeating things and what. Different ways, folks. Remember this. To accomplish different tasks. You get that? Now, what does the theorem or the principle state? It states that if there are n ways of performing one task, perhaps task 1, and m ways of performing task 2, we will then have n times m different ways of performing the two tasks together. Right? That's just the essence of all of this. Right? And of course, folks, I would say please remember logic here is key. I'll just say logic is key. Ne? And again, if you may think about logic for those who are wondering, because a lot of things go misunderstood while we're thinking we've got it all under control. So what is logic in essence? Again, folks, please learn to study things properly. It is a study, okay, of correct reasoning. right? Focusing on drawing. Goodness, andazi ngivele ndibhale into endingayazi nam. Focusing on drawing, what is this? It's a study of correct reasoning, focusing on drawing sound inferences. Okay? And I'm trying to be as, is it dogmatic? What do they call it? I'm trying to be as procedural as possible. It's a study of correct reasoning, focusing on drawing sound inferences and making valid arguments. Okay, you can just say making valid arguments. Okay, please guys, sometimes especially when you're revising, you want to structure everything. Remember when you're reading for the first time and studying things for the first time, it looks a bit fuzzy. Everything is just too vague at times. Or you can follow this part and that part feels out of place or perhaps very vague in the background. But when you revise, you want to put structure into what you can do and what you know and what you understand. Because once that is done, I swear to God, you will do more than you could have done before you did that. So guys, this is the very important thing. See here, keyword here is correct reasoning. It's not just reasoning, because a lot of people just reason and they don't realize that that's incorrect. And of course, how would you define correct reasoning? That's another issue on its own. But in essence, this is all about correct reasoning. And the correct reasoning, in my opinion, or in my understanding, or in at least the way it is expected to be, is to reason around facts, not just imaginations, okay? That's very important. So correct reasoning, and we're talking about drawing sound inferences. You get it? So when we draw sound inferences, it means at the end of the day, you just do something in a correct way by reasoning correctly. From there, you kind of draw an inference and say, okay, if this works this way, it means it will always work that way, no matter what. You see, those are kinds of inferences that you can draw from a correct reasoning standpoint. And from there, we can start to make valid arguments, you understand? Because when things look somewhat different, from the basis of correct reasoning and drawing correct inferences, we can then make some valid arguments around a given idea or point. All right, guys, that was just to introduce the topic in essence. Otherwise, there is not a lot to say or to teach in terms of theory, but we will just demonstrate what is in this topic in just working through some problems. So we'll start taking our first question. Again, folks, if you are interested, I will make this document available. Lately, I don't know, guys, what Wednesday can do. But I'm tired most of the time, hey? So I'm a bit agitated. I have what we call an increased psychomotor activity. So in a way, I just tend to become agitated when I'm doing something and it seems to be stalling. So I'm losing my patience day by day. And yeah, it's not good. Anyway, folks, let's look at this question 1. What does it say? A dog runs through 2 fences, right? So can you see these 2 fences? We can consider them as 2 tasks in a way. One has 3 holes and the other has 4 holes. Now the question says how many different ways. As you can see, guys, the fundamental counting principle is heavy on different ways. Okay? Different ways, not the same way or similar ways. It's all about different ways. If you can keep that in mind, you will never go wrong here. All right, so it says how many different ways can the dog run through the 2 fences, right? The other one is 3 holes, so there's 3 ways, right? Because you can use either one of the 3 holes. And the other one has got 4, so again, it can just go through any of the other ones. So in essence, by definition, if there's n ways of performing one task, that is going through the one fence, and m ways of doing yet another task that could be going through the second fence, then the result would be a combination of the product of the 2 different ways, where we can say that would be the total number of ways in which all these tasks can be accomplished together, right? So this is not a very difficult question. So we can say the number of ways is going to be the 3 holes times the 4 holes, isn't it? Which is going to be equal to 12 different ways. Okay, ndifuna ubhala kahle ke tana qandazi ngiqhela kabi nalento. Okay, I just don't know how to write properly, guys. Like, seriously, now it's getting out of hand. And I still have a lot to do, in life, and I'm worried. Okay, so guys, this is nothing but the principle. As you can see, if we understood the definition, we are essentially all good. So this is just the definition. So this is not a complex question. Of course, some questions force you to think overly, and maybe that can be a bad idea sometimes, but please don't forget basics. You know what I do all the time? If something gets too hectic for me, I go back to basics, because there I will not miss what is hiding. Okay, no issues there. Let's just take a second question. I'm just going to bunch them into one page sometimes. So here the issue is more of the demonstration on how to get things done rather than the teaching per se, Now I told you that at a restaurant, there is a choice of 3 starters. How many? 3. That could be mushrooms, soup, or pate, right? And 4 main courses. That could be chicken, beef, fish, or vegetarian, right? And we've got 2 desserts. Could be ice cream or trifle. Right, so again it says how many different combinations. You see, again, different combinations. Again, we said if there's n ways of performing one task, n ways of performing yet another task. Now we can add a third and say p ways of performing yet another task. Technically, the combinations here is going to be the product of all the 3. And remember, at this stage, we're not putting any order into this. It's not like a sequence of events per se. So in this case, this is called combinations, because when we calculate this total number of ways, different ways, when we don't put any order into this, meaning it's not like a sequence and series type of a thing, then once there's no order necessarily considered there, we just call it combinations. But when this kind of a situation has to follow a particular specified order, that would form more like a sequence. We call these permutations. So the difference between permutations versus combinations is an issue of order. When we calculate the total number of different ways in which we can do something, and there is no order specified, that is called combinations. But when we do the same task where order is to be considered, then it is called permutations, right? So don't get thrown off your balance by such terminologies. Right, anyway, so we can see that again, using our fundamental counting principle, so the number of different combinations is going to be equal to, we say there are 3 starters times 4 main courses times 2 desserts. So this is going to be 24. That's going to be 24 different combinations. Oh, my stomach is making a growl now. I don't know why, because I'm not hungry. So why is it growling? It's naughty. It's trying to mess up my video. It knows my tablet is too sensitive. It hears everything. So yeah, I'm sure you can even hear the little bugs outside making noise. Omaqhumpela, sithi ngomaqhumpela. Ndiqhumela nkongo abana. Akitsebe hekasikhuwa hore ba re ke eng. Maqhumpela yintoni ngesingesi. Andiyazi. So ilanto eqhumpayo is that bug that can jump, the black one. The noise you hear is that maqhumpela. Yeah, siqhumela nkongo he batsho baSotho. Right. So guys, again, a very basic question just to drive home the idea of, calculating combinations per se. Because here we have not put any order into which we want to do this. But if we start by saying the first task should be, say a starter, followed by a main course and then 2 desserts thereafter. If we start to put a particular order in which we want this, we would call it a permutation. But again, if you think about this, in a restaurant, what do you eat first? Do you eat dessert or do you take starters first? Perhaps starters, yeah. And then follows the main course. And then, of course, the last thing you would eat would be a dessert. So that's some kind of an orderly thing. But what if I just chose I want to eat one of the desserts? Would they stop me? Well, it would depend on where exactly this is. If it's some event that is organized for some people who decide what comes what and when. Something like that. So as you can see, this could be a combination, could be permutations, but in essence, we didn't really put any order here. We just decided this is what is available in this restaurant. So how many combinations can you make? See, not necessarily putting order that much into the equation. Right, folks? So I think this is not needing any further invitations. So we just do our job as we are supposed to do. Nice and easy. So let's get another question going. So question 3 says, the digits from 0 to 9, and we know they are in total 10. Please, guys, pay attention to totals of things. They make a lot of difference in sorting problems in this topic. Now, they are to be used to make a 10-digit code. Can you see? There's a specification of this code of how it should be. 10-digit code, all right? Now, determine the number of ways to do this, given that the digits may be repeated. Now, we can repeat the digits here. Now, we know that, okay, 3.1, the manner in which we answer this, the best way is to find the grid. What I do, I just go, how many things do I want? 10 digits. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So master the grid technique here. Create a grid that satisfies what is given. This is the little bit of manual labor that you're going to do. At the end of the day, it helps one to do a smart calculation much faster than to really struggle throughout the entire day. But here's what I would suggest to you guys. Again, if you just want to find out how to get this done, you can think about, say, when you're given a long thing like this where there's 10 possibilities or 10 digits to think about, just break it to 2 digits perhaps. Then you do this manually so that you can appreciate why we are going to do what we'll do when something is much bigger. So it always helps to model. So even doing the grid is some kind of modeling. And even if you further break that down into some smaller something that you want to study, and once you study it and see something about it, you can then transfer this into a bigger thing. That is when we're making, inferences now. Okay? So those are sound inferences in essence. And then once we do that, we then start making valid arguments, which would be, saying that in a situation like this is what you can do. And if somebody does something that is rather off, you can actually argue against that, because now you have a very, very strong framework on which you're basing your judgment. Right, now folks, if we can repeat, this means for this first option, first position, we can have all the 10 options. But if we can repeat, it means we will always have 10 options for each of the positions on the grid, right? So this is exactly what we're going to have. And in essence, how many is this? These are 10s. So this is 10 to the exponent 10, okay? Right. So 10 to the exponent 10 is definitely going to sit with the scientific notation because there's just too many zeros there. So once the zeros are too many, then we will end up with a situation, right? I think if they surpass 10, which is the case here, then we end up with the scientific notation. Even if you put it on the calculator, it's just going to say 1 times 10 to the exponent 10. Right, so this is different. Is it different? I wonder. Okay, they will be different. You can repeat a digit, but this one is going to be different from the other. And we'll never have repeats. So yeah, this is different number of ways. Okay, different ways. Or you can say number of ways. It's not a big deal exactly what you say. What matters here is the calculation. So as you can see, this is the case, guys. Again, you may sit at home and be like, but hold on, this doesn't sound right. Now, what you can do is to do this manually. But again, the best way to do it manually is to break it up and say, for example, you want a 2-digit code where you can use all these digits, you know. And if you do that and you start doing it manually, you will start to see that indeed this rule will hold true. Well, what we'll have here is going to be 10 squared, which is 100. But of course, that will take you half of the day to sort out, I guess. Anyway, that is just me trying to force you guys to try to find sense in what you do. I can tell you, folks, you can sit at home and solve a ton of question papers on any topic that you choose. If you are not realizing something in that process and you're not actually finding some sense in certain ideas about the topic, then you are wasting your time, because when the questions come in the exam, they will be twisted and you may not see them again despite all the effort. So when you put your effort in the wrong way, you are the same as someone who's just sleeping and not doing anything, because you will be crushed. At least that person may have an excuse and say, well, the reason I didn't do so well, I actually messed around. So they may even be motivated to do it again. But you who have done so hard a job of trying to study and make notes and stuff, and then you go and write and you fail, it's going to be more hurtful. It might actually demotivate you from going forward. So it depends on how you do things, guys. What determines, your outcome at the end. So in my opinion, don't just answer these questions. It's easy to answer them and get an answer and celebrate, yeah, I've got it right. But do you understand what is going on? Do you even have any idea of how this works? So this is why I would say, once you do this, try to model this a bit. Sit back. Study these things, because trust me, in the exams, there can be a few little ways in which these questions can be phrased or structured. At the end of the day, it all anchors on the on the basics. So get the basics right. You will get this right. So in my opinion, I would suggest to you guys that please model this by taking, say, 2 digits. Make a 2-digit code where you can repeat. Then do it manually. Please do it manually to prove that indeed what you're going to get is going to be 10 squared. So that you can see that, okay, every time you have a similar situation like that, that kind of an application would work. Okay. Now 3.2 says the digits may not be repeated, but what do we have? 10 spaces. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this time we're not going to repeat. So for the first spot, we've got all 10 options. But once we put down 1 there, then we'll have 9 options to choose from. Once we put down the first 2, we're going to have 8 options to choose from. And then they keep dropping by 1. Okay, and remember, we are multiplying here. These are combinations in a way. Now you may decide that, okay, you're gonna say, is this, remember now, not repeating is somewhat putting some kind of an order in this, I would assume, but again, it's not really a big deal. So this is basically 9. Sorry, it's because it's 10 times 9 times 8 times 7 times 6 all the way to 1. So this is what we call 10 factorial. And again, go and check what a factorial is. Know the definition of a factorial. Know it even in its generic form when there's no number, so that when a question comes in that format, you can recognize this is a factorial. Please, guys, there's no excuses you can make here. So let's see, 10 factorial. For those who don't know how to punch this on the calculator, you just press the number 10. And then you go to the shift button. And then once you press the shift button, you go and press the inverse of X button. It's written like that. It's near the log on Casio calculators, usually below the mode button. But again, it can be anywhere as long as you know this. Usually at the top, it has that factorial notation. That's how you unlock it. And then once you do that, what you end up with, it writes on the calculator like this, 10 factorial. Then you press the equal sign and get the answer, okay, which is what we are about to do. So this is 10, oops, it's off, 10, shift, we press that inverse of X, it actually punches that as 10 factorial, then we press an answer, we get, this is 3 million, again, please guys, learn to read numbers, don't embarrass us, eh? When you become ministers here and you can't read numbers. You will embarrass us. Simply 3628800. Again, these are all gonna be different ways, because we know that the fundamental counting principle is all about different ways. We don't want the same ways. Okay. So 3,628,800 different ways. So that's a 10 factorial. Okay. Now, folks, perhaps this is, the right moment to really show you things that you can do. One can use what we call the permutations button. Permutation button to do the same calculation. So with the permutations button, you count how many spots do you have. Ne? So the spots that we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so there's 10 spots. But now how many options do we have available to choose from? We know that it is 10 options there. So we take the number of options. By the way, this button is written as NPR. So basically, this is the options available, and this is the spots to fill, meaning the positions on the grid. So we will write 10, and then what we do, we then press the shift key, right? Remember, you will look on the calculator, you'll see that anything that has the color of the shift button on any of the recognizable buttons, it unlocks that function when you press the shift key. So this is going to be the shift key, and then we press the times button. If you look at the times button, it's written NPR on top. Okay, so what we end up with, it's going to actually insert this special permutations, which is P, like that. So I'm going to say like that. That would be the P. And then we follow by R. R is the number of positions to fill. Remember, 10 is the options available. The R is the number of positions to fill on the grid. So we have 10 spots as well. So that's what we write. And then we press the equal sign. Okay. So let's see if I cannot move this down here, just to make it nice and easy to see. Okay, so this is going to essentially give us, let's see if it really works. Sometimes I haven't checked certain things, but yeah, you will see that these things work. Okay, gives us the same answer. So this is 3628800. Oops. Right. So obviously, guys, when you write this down, the way in which you're going to present this, if you ever did it that way, I suppose you would write 10p 10, which is going to be equal to 3628800. Right. So this is very important, folks, to get this job done. Okay. I hope we are doing well, because if we're not doing well, we will do badly. Okay, please know how to use this permutation button as well, because sometimes you may not want to waste time. I suppose this is the way you would present an answer in the exam, because the part here is just the actions you need to perform in a way. All right, as you can see, we get the same answer. Get 3,628,800 different ways. Remember, permutations or combinations all about different ways. Difference between permutations and combinations is that combinations have no order. It's not a sequence of any events whatsoever. We just put all of those total number of ways in any order we choose. But the moment we put an order into that, it becomes a permutation. Nice and easy, isn't it? Yes, of course, it should be easy. If it is not easy, you are dead and to be buried. Great stuff. As you can see, the moment we start to put some restrictions in there, like we cannot repeat digits and stuff, you will see that the number of ways drops from the random way we could do it if we were to repeat anything at all. So yeah, you will start to see that the more restrictions you put, you expect lesser and lesser outcomes. If you get more instead, then start to worry what happened. But again, some issues and situations can actually do that. Okay, be very flexible. Right, guys, I know I'm gonna talk and talk and talk. Let's just keep going. Maske sitinje, go on. Question 4. Right, as you can see, repetition becomes an exponential kind of thing. No repetition becomes a factorial of some sort. Right. Now question 4 says digits from 0 to 9. Again, how many are they? They are 10. Are to be used to make a 6-digit code. Can you see now? The number of options available, they are 10, but the number of spots to fill, they are 6. So this is R. I'm on some papel. One again, pale. This thing, I don't know, it has some functions I don't know. The number of options to choose from, which is n, that's 10, and yet the spaces to fill on our grid, it's going to be 6. Can you see there's a bit of a mismatch here? Now the question says, determine the number of ways to do this, given that, digits may be repeated. Right, so we have 4.1. Now we can make our grid 1, 2, 3, 4, 5, 6. Remember, that is the number of, the grid positions we need to fill from 10 options. Now when we repeat, it's going to be all the 10 options here, like that. And we can see that this transpires to be 10 to the exponent 6, right? And we know that 10 to the exponent 6 is 1 meal. Once you see 1 and then the exponent there, it means the zeros are going to be that many. So the zeros are as many as you see the exponent when the base is 10. Yeah, it's going to be 1 and as many zeros as you see on the exponent. Again, these are some observations, guys, you need to start to notice, okay? Please. Can you see 10 to the exponent 1? There's only 1 0. 10 to the exponent 2, there's going to be 1 and 2 zeros. 10 to the exponent 3, there's going to be 1 and 3 zeros. So these kinds of things, please keep in mind. Keep in mind, okay? Okay, now there's going to be a million different ways. Right, these are all different. We're not putting an order per se. You can call it combinations in a way. Right. Now, we've answered that first question. So the next one is 4.2. Says the digits may not be repeated. So again, we're going to have 6 spots on the grid. 1, 2, 3, 4, 5, 6. Now, first we will have all 10 options for the first one. But this time we're going to have 9, 8, 7, 6, 5. So this is what we will have. Count 1, 2, 3, 4, 5, 6 years. So this means we are multiplying these together. So this is basically 10 times 9 times 8 times 7 times 6 times 5. Right, let's do it quickly. So we have 10 times 9 times 8 times 7 times 6 times 5. So this gives us 151,200. This is different again. Different ways. Please remember that. Of course, here at this point, we really did not put an order per se, but so you could consider this as a combination rather than a permutation, but however you look at it. Great stuff. So please, guys, again, I'm emphasizing these things so that you remember this, because you never know when things will change on you. Great stuff. So this is cool. But when we observe the situation here, we see 10, 9, 8. As you can see, these things are decreasing by 1. When they're decreasing by 1, they want to look like a factorial. So in essence, we can use the factorial notation to sort things out here. So we can say using factorial notation. Right. So when using a factorial notation, we'll just say this is simply 10 factorial. Now we take the leading number or the leading digit, because that tells us the total number of options, or you can even consider that as the total number of options is going to be a factorial, right? And then we divide by the very 10, but we subtract the number of spots on the grid that we needed to fill, right? So we'll just take the total number of those options and subtract the spots. Now the spots are those positions. So there's 6 of them. So we subtract 6 and we say that's a factorial. Now you will notice that we'll get the same answer as we did get above. Okay. So this is going to be 10 factorial divided by 10 minus 6. And of course that is also a factorial. And indeed we get the same answer as we anticipated. So if the action is correct, guys, the answer is going to be the same. Okay. So this is cool. So as you can see here, okay, we can use the factorial notation once we notice what looks like a factorial. A factorial is when you've got a leading whole number multiplied by the next, which is 1 less than itself, and so forth, like that. That becomes a factorial. So that means we can think of a factorial notation. But since this is not complete, we then have to kind of sort this up with that. Okay. Now, my students know why this works, okay? If you're not one of my students, well, I'm sorry. You go and find out why this works. Okay? Right. But let me be friendly to you and not be too brutal. You know, sometimes to be brutal is not good. 10 factorial, we know that it's going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, what is this? 10 minus 6 is going to be 4. So this is 4 factorial basically. So 4 factorial is going to be 4 times 3 times 2 times 1. Can you see when we do this division, this dude takes care of that dude. They divide to 1. And guess what survives this whole situation is exactly what we have over here. Can you see that? So that is why we can actually logically, because this is part of logic. It's not necessary for you to do this, but it just says logically we can make this inference because it's a sound inference, right? Because if we can notice that if we're doing 10 decreasing by 1 up until 5, it's the same as saying, well, this was 10 factorial divided by 4 factorial. In essence, gives us the same answer. So this is why it works. So this is just a logical thing, because those who studied these things, they did what we just did now. Then they kind of gravitated towards that particular formula, which is what you would call a sound inference. And in essence, it works. Okay. So guys, this is just an option of how to solve the same problem. And as I said, when you study things, take time. Study these things properly. Don't just go through the motions. You can do 20 question papers and perhaps get the answers right and go and fail the same question on probabilities in the next exam if you did not understand. Because remember, even if we repeat those questions, we will twist them a bit. We're not going to just repeat them the same way unless you are truly lucky, which has been the case in some exams in the past. You find that the same question is given with the same diagram or same question itself, you know, as it was in the previous papers. Sometimes it happens, but what if it doesn't? And what if this is your final exam, which determines your future? So please, guys, don't toy with your future. Take chances as they come. All right. So that is when we're using factorial notation to solve something that is somewhat looking and giving the vibes of a factorial. It's not a must, it's just a suggestion, and you can see it goes back to the definition of logic, literally. Now let's say we have yet another option that we can do. Can we use our permutations button? Because whenever you see this factorial thing, you can actually use the permutations button. I can already tell you that if you can use a factorial notation, you can use the permutations button to sort this out. So now let's see. We know that we've got 10 options in total. And then we insert our lovely P. You should know already, I stated how you do that. You press the shift key and press the times button. It has an NPR on top. Then it will insert this P. But now how many spots on the grid do we have? 6. So we just write a 6 in there, and then you press the equal sign, okay? So this is going to be 10, shift, don'ts, and then we get the same answer. So this is 151, 200 different ways. Okay. So this is using NPR button or key, whatever you want to call it. All right, guys, so I'm doing this deliberately to force you guys to make these notes. It doesn't help to just solve and be happy you can solve. If you don't understand what you're doing, you're going to get caught up. I promise you. And when you get caught up, you will not be able to solve a problem. Because sometimes the very same problem that you could solve in this way? What if it's given to you in this manner? And you have to make some justification of some sort, How would you undo all of this and take it back perhaps to something like that on the grid? Things like that. You need to know these things. You really need to know this thing, So somebody may give you this and say, write this in this manner. What would you do? Or somebody gives you this and say, represent this on a grid, and maybe give you an example of how the grid should look like. Then you get stuck. But if you take time to understand things, you'll be like, wow, this is just a classwork. But to others, it will look like a mountain hike, Anyway, not talk too much. Let's do more. All right. Of course, guys, we're going to just build our confidence nicely. And I just hope you will have the patience to go with me all the way across the river. So let's do question 5. So question 5 says, determine the number of ways the letters of the word equations can be arranged. Now, when you're given a group of items, look at this. So this is why I said most of this, oh, sorry guys, I'm moving a lot. Maybe my voice may be sounding like it's going away, or maybe it's too close or something. I'm just a guy, man, who forgets that I need to stand still. I'm not one of those people who just stand still. I have an increased psychomotor activity, so I move around unless I'm asleep. Right, the word equations. Now, what is important is to find the total. Always focus on the total. How many words? How many letters this is? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there is 9 letters here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Very important, because that is the total number of options available for us to choose from. And we are told we want to arrange this. So if we want to arrange this and there was nothing mentioned like we want to make perhaps say a 4-letter word or maybe a 2-letter code or something. So in essence, if nothing like that is stated, it means we just want to rearrange the letters, as you can see, arrangements. So it means we just want to rearrange those letters. How many times can we do that? How many arrangements would we have in total? So this is very important. So this is now becoming a very tough question. Now, the second thing that you guys want to know when given things like that, either digits or letters for that matter, you just want to answer a question. Are there any repeated letters? Are there any repeated letters? As you can see, E is not repeated, Q is not, U is not, A is not, T is not, I not, O not, N not, S not. So the answer is a big no. And if it is not the case, then we don't have to worry about anything. Their number will give us the factorial, that's all. Just remember that. So to answer this, we're going to have 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we will have all 9 options for the first. Then as soon as we put one letter down, we're going to have 8, 7, 6, 5, 4, 3, 2, 1. And what we can see here is just 9 factorial. Right. So that is very easy. So just say 9 factorial. And now we know how to do that. So this gives us 362,880. Right? Different arrangements. Remember, this thing is going to only give us different arrangements. As long as the letters are not repeated, we will always have different arrangements. Okay, if we do this. Remember, there are no repeated letters. So it means we're going to get 9 factorial different arrangements of those letters in the word equations. So very easy, straightforward stuff. And of course, those who know, we can easily write the total options we insert our special P, then there's 9 positions on the grid to fill when we're using our NPR button. So it's 9, shift the times button, and then we press 9. Still get the same 362,880 different arrangements. Okay, so that's the option for those who just like to go about business easy. Remember, here nobody tells you how you're going to solve. So even if you did that, if you get the right answer, guys, you get full marks. No issues. Unless something is clearly stated how you're going to do it, then you do it that way. Right. Now, let's get to the next question. So we have question 6. Now, question 6 says, a code is made up of 3 different letters followed by 3 digits. Okay. Now we know that if nothing is mentioned here, we're not going to worry. Sometimes when we say 3 letters, how many letters do we know? The total is 26 letters of the alphabet. And the digits, we know that they are 0 to 9. So in essence, these are 10 digits. So we know, okay, we're probably having this 3-letter code from all 26 letters available and 3 digits from all 10 digits available to us. But let's read on. Only consonants. See now, there's a bit of an order to this. Only consonants may be used. So there's a restriction to this. And they may not be repeated. Now we know that consonants are all the other letters except the 5 vowels. Right. So basically of the letters, we're going to subtract the 5 vowels. So this tells us now that the total of the letters we're going to choose from is 21. And then any digit from 0 to 6, can you see? Again, out of these 10, we're going to take away the rest of the 4. So we only remain with 6 digits. So here we will only have 6. So now this is a bit refined now. So this is 0 to 6. Okay, that's what we have. And in total, these are 6. Sorry, not 10. So please, guys, refine stuff. Okay, now it says any digit from 0 to 6 may be used and they may be repeated. Very important. So that means the digits can repeat. How many such codes are there? Right. So we will say, fine, we've got 3. So always master the grid, guys. We've got 1, 2, 3, because we've got a 3-letter followed by 3 digits. Maybe I can use a different color. 1, 2, 3. Can you see? There is an order. First we said letters, 3 of them, then followed by. Can you see? That is a sequence of events. Now this is definitely a permutation, not a combination. Okay, there is an order this time. What we've been doing above had no specific order. Hence it became combinations. But again, we could see that we could apply some permutations techniques depending on the structure that we could make. Right, now let's see what is cooking now. 3 letters, but now remember, we were told only consonants, meaning all the vowels are out of this picture. So basically we will have 21 for the first spot. But once we put down, since we cannot repeat the letters, we're going to have 20. And once we put the first 2 down, we're going to have 19 options. And that stops, okay, for the letters. Then we get to the digits. The digits can be repeated. And how many are they? 6. 6. So we will have all 6 for each one of those spots. And remember, we multiply these things. Now these are permutations. So at some point we can say this is 21 times 20 times 19 times 6 cubed, just to simplify our work. So let's do it nicely. So 21 times 20 times 19 times 6 to the exponent 3. So this gives us 1,723,680 different. Remember, this is always going to be different stuff. Different codes. Right. Great. So this is easy, guys. Very nice. Very straightforward. Now, for those of you who just want to explore things, be like, okay, how about we use our factorial notation, because we can see this friend is giving us the vibes. Yes, it is. So we can say this is 21 factorial divided by. Now, of these issues here, there's 3 spots, isn't it? So this is going to be 21 minus 3, and that is a factorial. Can then multiply this by 6 cubed. There's no other way I know how to express that. So in essence, let's see if we're going to get the same answer. Of course, this is a valid argument. It should give us the correct answer. It is supposed to. Okay? As long as we know how to look and where to look as well, we will always win. Indeed, we win. We win. So we still get the same answer. 1,723,680 different codes. Okay. Right. Now you may also want to explore the other way of using our permutations button. So we know that out of 21 options, we will insert our P, how many spots on the grid for that which looks like a factorial. There's like 3 of them. And then we can multiply this by 6 cubed. I don't know as yet if we can do something about that 6 cubed, which is special. At the end of the day, we just write 21, shift the times button, we put the 3, and then we just say times 6 cubed. And we get the same answer. So this is 1,723,680 different codes. Can you see, guys, small steps that are heavily understood will really make you prosper. But again, is your choice, folks. I'm just going to throw this to you because at this point, we are revising. Not interested in just solving problems for you, and you are just impressed. At the end of the day, you get a question in the exam and you can't do it because you didn't understand what you are doing and why you are doing it. Okay, great stuff. So please, guys, master these things that I'm showing you. You will go far. So you can see that we are really building on our logic and our confidence here. So let's do question 7. So there's quite a lot of questions and we're going to do all of them. Now this one says a code is made up of 3 letters followed by 3 digits. Again, a similar situation as in question 6. The first letter, can you see there's a bit of a situation now? The first letter must be a vowel. Thereafter, any letter may be used. Can you see? And any digit from 0 to 9, can you see all of them are back now? How many are there in total? 10. And how many letters are here? 26. And we don't have a restriction on the letters as well. Okay, may be used, but the last digit must be even. Very important restrictions now. How many such codes are there? Okay, we do the grid thing. 1, 2, 3 letters and then followed by 3 digits. 1, 2, 3. Right. Now remember, when there are restrictions like this, we start with the restrictions. Now this is the technique that one needs to understand. When there are restrictions, you consider the restrictions first on the grid. Then the rest falls into place and the rest becomes correct if it is well constructed. Now let's have a look. we are saying the first letter must be a vowel. How many vowels do we have? There's only 5, right? A, E, I, O, U. Zizikhamiso. Kuleya ngaphezulu question besithethe nge-consonants, which is osinga nkamiso. Bangathi ukhamisile kodwa ukhamisanga. But vowels, they force you to open your mouth. Huh? And there's a shape in which your tongue is going to be on the floor of your mouth. Very important. The tongue is flat on the floor while your mouth is wide open. That's vowels for you. But consonants, you are almost like, but the tongue is not really assuming the shape that is flat on the floor. The mouth is not really wide opened. Yeah. So now we're talking English and maths, right? Yes, because these two are both a language. So they will come together somewhere. They will intersect or overlap. Right, now vowels, we've got 5 options because there's only 5 of them. So that's why on that first position, we can only choose out of 5. Right, now that's good. And since we cannot repeat, the first letter must be a vowel. Thereafter, any letter may be used. Okay, not a problem. Now, folks, here's another thing that we have a problem with now, is the fact that there's no mention of repeating and not repeating. This is a bit silly and scary. But if you think about it, repeating is some more of a conditional situation. It's not a natural situation. To repeat things is not necessarily a natural thing, I guess. I would put it so. Nature tends to recycle rather than to repeat. I don't know if you get me. It's more of a cycle. Whatever point we pass, we're going to pass again. But it's not necessarily a repeat. It's more like its own thing happening in its own time. It's just that it's similar to what has happened before again. But naturally, repetition is not really a thing, So technically, you think about the natural situation. When nothing is mentioned, you don't assume an unnatural position. To repeat things, it's an unnatural thing, to be honest. Although it is present, but it's more of a conditional thing, right? So if the condition is not provided, we're not going to consider it, okay? So that's my opinion about this question. Again, I could be wrong. You find out about it. But whenever I get situations of this nature, I just sit back and be like, okay, in a natural sense of things, is a repetition something that is a must? And is a no repetition something that is rather conditional? Now, if you look at it, we don't necessarily repeat, Nabazali bakho xa bethole wena mfethu abaphinde bakuthole again, the same person. Bazathola omnye umuntu. You get it? Yes, izofana into because ngabantu at the end of the day, but it's not the same person. You get it? So, but amawele, they sometimes can just show up with some identical twins. But can you see it's a conditional thing? It's not really something that you would say is a given. Everybody can. As much as they all hold a potential, but it depends on a certain situation that leads to that effect. But the natural way is one child every time. One pregnancy, one child. Okay, I hope we understand each other, guys. So for me, if we put down any of these vowels in there, mind you, out of 26, we now have 24 options. And then 23. Now we get to the digits. Again, with the digits, nobody told us about repeating and not repeating, right? So in essence, we just first deal with the part that says the last one must be even. Now, of the digits, how many are even? 0, 2, 4, 6, and 8. As you can see, these are all 5 in total. So we can have 5 at the end over there. And now after that, it says any of these digits may be used, right? So after 5, once we put down 1, we will have 9 and then 8 options, okay? So again, folks, you may ask, why are we not repeating? Because nothing was said. Remember, as I said, in a natural sense, we don't necessarily really repeat. You can't have 0, 0, you know? Yeah, we don't really think about that at the beginning, for example. And then 1, 1, and then 2, 3, 4. When you count, you don't say 1, 1, 2, 2, 3, 3. No. Just say 1, 2, 3, 4 through infinity. But if somebody decides now to force you to repeat 1, 1, you're going to do it, right? Because that's an instruction now. So if no instruction is given, we go the natural way. If then an instruction that is rather contrary to the natural way, then we adhere to the instruction, right? Yes. Yes, yes, yes. So that's my argument here. But again, guys, you go and find out what should be the case there. At the end of the day, I cannot claim to know it all. So this is 5 times 24 times 23 times 9 times 8 times 5. Okay, so let's sort this out. So this is 24 times, this is 5 times 24. Wait. Why did not 24? Why? 10 mundazobhala into engekho. Remember, we've got 26. If we put down 1, it's going to be 25. And then 24 here. Okay. So let's see. This is going to be 5 times 25 times 24 times 9 times 8 times 5. Right. So this gives us very interesting numbers. 108 0 0 0 0. Yeah, different codes. Okay, so that's it, folks. This is what we're gonna get. And now, what is that number? What is that number, bafowethu? Yeah, so are you gonna say this is 1,080,000, or you're gonna say this is 10,080,000? What are you gonna say? You tell me. You're gonna tell me, right? Right. Yeah, this is interesting, but this is technically 10,080,000. So this is 10.8 million. Okay, good. That's fine, folks. Please learn how to read digits, or at least numbers, big numbers. Embarrass national television. Anyway, guys, so that is the one. Okay. Now you may want to argue, as I have shown you guys. You can see that 25 to 24 is 1 less, as well as 9 to 8 is 1 less, and that product smells like a factorial. So you may want to also use that, because sometimes you will see certain things on the memo that don't make sense, and you'll be like, what is this? So we may have here 5 times, instead of this we can say 24. I don't know what I did here. This is wrong, guys. So this is 25, 24, yeah. Right, so this is going to be 5 times 25 factorial. But now we can say that this factorial right here has got how many spots in there? There's just 2 spots. So we can say this is 25 minus 2 factorial. Times, again, we will see that this is also smelling like that fish as well. So this is 9 factorial divided by 9 minus 2, because there's just 2 positions there. That's a factorial times 5. Sometimes someone may combine the 5s and say 5 squared, and you'd be like, where did the 5 squared come from? So if you don't master the grid technique, folks, uzoba embarrassed. You will be embarrassed. So obviously, guys, if we are doing the right thing, we should find our answer to be the same. 108.8000. Different codes. Okay. So sometimes someone may decide on the memo to just write it like this. And you'd be like, what? Even that 5 and 5, they'll be just saying 5 squared. And you'll be thinking, where did the 5 squared come from? So folks, this is why you can't just look at the memo and think you're going to understand. Please learn. These channels are not here to just decorate YouTube. No. We have better things to do, folks. But we are not here also for popularity. Don't get it twisted. It's not a popularity contest. This is a concern for the state of our nation's education. Basic education, at least. Because we feel there are some gaps, and these gaps, unfortunately, remain unbridged. Why? Because the bridges to these gaps sometimes are not possible with what we have available. It takes people who have gone through more than just the matric level of study, and perhaps who are even doing things that are beyond just even university level of study in a way, then to come and share those ideas. So don't find these little bits and pieces of what we share as insignificant because they don't seem to feature in your textbooks and stuff. These things can ensure that you win most of the time, certainly not all the time. And here it's not about winning all the time, it's about winning most of the time. Because this is what ensures you progress. No matter what the situation confronts you, you will always confront it back and perhaps succeed in your quest to defeat it. Okay, let me not talk, guys. I like to talk, but you see, most talking is not so fun. Some people get bored. They're like, what the hell is this guy doing? At the same time, we can say this is 5 times 25 special P and a 2 there because there's 2 positions for what would look like a factorial for the letters, times again 9, as you can see there, and then our special P and then 2 because it's just 2 grid positions there for what looks like that factorial, and then we can put that. So again, we're gonna get the same answer, 108.0000. So as I am going through these questions, folks, I'm forcing you guys to really understand what's going on, okay? I'm really forcing you guys. And you can see all of what we did. I showed you the reasons for it. So there's no questions about it, okay? I'm just trying to make sure that if the memo comes out looking, of course, the most likely way it would look, if it didn't look like the first part, it's going to be that. This one has not really been part of, it's not really been part of the works part. You can present the work that way. Nobody told you not to do it that way, okay? But whatever you do, make sure it's perfect, because if it is wrong, you even lose marks where you could get marks, perhaps making a mistake at the very end. This one, if it is not done properly, you lose all the marks. But if you know what to do, you can do it. Even if there's too many marks to be considered, you will get all those marks automatically because one can see what you've done. Yes. Okay, guys, so this is the best thing I can do here. But I feel that question 7 is incomplete because we were not given information about repetition versus no repetition. But again, think of the natural situation rather than a conditional situation. Okay, good. Right. So this is question 8. Please share your ideas about that question 7 if you have a differing opinion. Right. Everything is welcome. Comments, suggestions, criticism, whatsoever you have. Right. Question 8 says the letters of the word pandemic are arranged in any order. Right. Again, we studied this. How many are they? 1, 2, 3, 4, 5, 6, 7, 8. So they are 8 in total. So that means we have 8 options available to us. Okay. It says determine the number of unique arrangements. Of course, unique is another way of saying different. Okay. Unique arrangements that can be made. Again, can you see there's no constraint as to saying we want to form maybe a 3-letter word out of all of these. This time, nothing is said. It means as 8 as they are, we're just trying to rearrange those letters to form different words. But those words are going to be 8-letter words. Right, so 8.1. Again, we master our grade 1, 2, 3, 4, 5, 6, 7, 8. Of course, the next question is, are there any repeats? Are there any repeated letters there? We can see P is not, A is not, N, D, E, M, I, C. So the answer is a big no. So once that is a no, we know that, in general, when there's nothing that is repeated, so this is certainly going to be the total number factorial. Yeah, it's going to be 8 options, 7, 6, 5, 4, 3, 2, 1. Right, because we cannot repeat, by the way, because whatever we have been given, it's all we can use, isn't it? So this is 8 factorial. We already know how to do that. So 8 factorial is 40,320. So this is 40 squared 33 and 20, okay? Different. Oh, by the way, the word was unique. You know, sometimes you use what was given. Stop manufacturing your own things. Unique arrangements. Ne is on. Right, folks. So again, you know what? In the interest of time, I'm not going to repeat these other issues like, you know, using the factorial notation. But I mean, the factorial notation has already been taken care of. How about using the permutations button, you know, things like that. But hey, sometimes I don't want to allow you guys to be lazy in thought. So this could be same as 8, P8, isn't it? Because there's 8 positions on our grid. We're going to get the same answer. Abana mangangane awalali ayafundekela nasebusuku. Ezintaka ndizange ndaziva zifundekela ebusuku before. In my life, guys, ndakhula ento ezingarasi ebusuku. Intake besizazi okanye into efana nentake bingamalulwane nezikhova ke. Leya mangangane awafundekela ebusuku. Andi understand at all. Sesibhanqe ezitheni ezingalaliyo ezi. Inoba sekukhona ukuthakatha khona lapha ngisayiqondi kahle. Anyway, beloya benjalo akhonto bazoyenza pha kum. Right. So 8.2 says determine the number of arrangements if each word must start with the C and end with an M. Now more restrictions. So again we have 1, 2, 3, 4, 5, 6, 7, 8. Now if we're starting with the C, there's only one C there. And if we're ending with an M, there's only one M. Remember, you start with the restrictions on the grid. The rest will come into place. So now we've got, out of 8 letters, we've taken down 2. So we're going to have 6, 5, 4, 3, 2, 1. And we certainly cannot repeat, because it's just a rearrangement, if you will. So this is 1 times 6 factorial, isn't it? 6 to 5 to 4 to 3 to 2 to 1, and that's a product. It's a factorial, right? Times 1. This is essentially 6 factorial. Sometimes you will see on the memorandum, you'll just see 6 factorial and you'll be like, what? Yes, it's because someone is just taking the essence of what you have there. But it's not how you structured it on the grid. So master the grid, folks. Nothing is ever not going to make sense. So 6 factorial is 720, isn't it? Yes. So we've got 720 different, unique, unique arrangements. My arrangements is dead, but yeah, all right, a fair and jar. Okay, guys, so you can already see here that you've got options of words. So you've got options. You can say, for example, this is 1 times. You can just say 6, lovely P, 1, 2, 3, 4, 5, 6. You see? 6 factorial is like that, and then times 1. And of course, someone may just say 6, special P, and 6, and that's going to be 720 unique arrangements. Right. So bafowethu, that is essentially what we are expected to do here. Very easy, not complicated. If we follow the structure of how to do things, which is technique based, we will not go wrong. But if we start pfeffering around, not knowing what we are doing, we're gonna die. And that's our choice as well, so we can respect that, right? Determine the probability that each word starts with a C and ends with an M. So this one anchors on 8.2. So we know that the probability of our event E, as described in the question, is going to be the number of ways the event E can be expressed divided by the total number of outcomes in our sample. Now this is 720 divided by, when we did not have any specific arrangements necessary, when it was just a combination. So this is going to be our 8 factorial, of course. So let's see what that probability is. So these are very nice questions because they kind of build one up to that probability. But be ready to face a question that just jumps for that 8.3 given the statements of question 8. Question 8.1 and 8.2 not being asked. It can happen. This is how the very same easy question can be converted into a silly question. Okay? One can just choose to ask only this question for that question 8. Given all that, then you have to figure out the unique arrangements with no restrictions, 8 factorial. Then you figure out the number of ways to express the given condition. That would be what you get in 8.2. And then perform the probability. Of course, this one would be more marks than it would be in this case. Right? No questions about it, guys. Again, this is more of an exam question. It usually gets asked this way when it is simple, standard grade stuff. But one can convert it into a higher grade question by just asking question 8.3 only. Then you figure out the rest as intermediate steps. Right. Let's go to question 9. Question 9 says, the letters of the word algorithms are used to form different 5-letter words. Can you see now? That's a different story. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. But now we've got 5 spots. So this is N10. This is R equal to 5. Can you see we've got limited spots versus more options available? You see now? Yep. So it says how many different 5-letter words can be formed. So we're going to say, well, not 8, 9.1. Gonna say we want 5. 1, 2, 3, 4, 5. And we're gonna have, of course, here we can think about it again. Is it likely that we can repeat a letter there? No. So we can say this is gonna be, if we put any one of the 10 here, then there's gonna be 9, then there's gonna be 8, then there's gonna be 7, there's gonna be 6 options there. Now that's it. So this is as good as 10 times 9 times 8 times 7 times 6. Okay, so this is 10 times 9 times 8 times 7 times 6. So this is sitting yellow. Go yellow. Samtola gota. Go yellow. Samtola gota. Ando. Yawana. This is 30,240 different what? No man, different looks hungry. Difference is 5-letter words. 5-letter words. Even Afrikaans kind of borrowed some words in English. Word. Goodness. Who originated this word? I don't know. But I know Africans borrowed it. So it's not only Xhosa that borrows words in English, eh? Yamos. Anyway, mos. We've got it, mos. Now this is the one. Or we can say this is 10 factorial divided by 10 minus how many grid spots? 1, 2, 3, 4, 5. So this is going to be 5 factorial. It's going to give us the 30 decent 200. Yeah, because yeah, injalo lento lena difference. 5-letter words. So the other one may think of the permutations. This is kibisela bantawet. So this is 10 special P. How many positions? 5 there. So ndifuna niyiqhele lento lena ngoba ukuba ngaba aniyiqheli izawuniqhela kakubi yona. Yibona yonke lento. Awufuni ukuqhelwa kakubi into engathethi. Izakwenza udomkop and asikufuni ube ngudomkop. Funeka yona ibe ngumdlalo. Differentius. Difference. Faith. Is it 5? Konje 5 ngubani? Is it? Yeah, 5. Okay, siphelile ke ngeSpanish sakhona letter word. Spanish sakhona sisiphelile khona lapho. Right. Now sidlule sigqibile. Now all these others guys are options. You see permutations, buttons using factorial notation. Whenever you can use factorial notation, remember you can also use the permutations button or key. Yes, you understand now. Says how many different 5-letter words can be formed using only one vowel. Can you see now? This is like, you wanna kill me, Messiah? Why are you trying to kill me now? Well, the thing is, hey, yabona yawenza siqhala kakubi lena. Thengathi ufuna siphambanela. Oh yeah, I know guys, siphambanela. Ayizosiqhela kabi. I saw sithi qha bangaziqhela kabi yafumana. Anyway, we still want 5-letter words. 1, 2, 3, 4, 5. Now this one is a bit hot, as you can see. It has only one vowel. How many vowels do we have here? Now this is coming. So A, O, E. So those are the 3 vowels. So there's only 3 options for a vowel. But remember, the vowel can be anywhere. You understand? It can be anywhere. But it's always safer to just hoy it in the first position, because you know what? If you try anything else, you're going to break your neck. So we can only have 3 options for that first spot, considering that that should be the position for our vowel. But remember, this is a loose position. It's not fixed. Maybe I should even show you this. Sorry, this way. That this is a loose position. It's not fixed. It's not. We are just loosely fixing it. Say, okay, sit there. We've got 3 options for that first letter if we are choosing that. Now, then after we've put down 1 letter there, how many do we have? But remember, the case here is that only 1 vowel. So now this means the next positions are only going to be filled by the consonants this time. Okay, how many are they? So we had 10, we subtracted 3 vowels, we left with 7. 1, 2, 3, 4, 5, 6, 7. So this is going to be any one of the 7, right? Yeah, it's like that. But remember, in this scenario, nobody said the consonants must be together. You get it? So this means our friend can be where we see it, or it can occupy the 2nd position, the 3rd position, the 4th position, the 5th position. Because it's a loose cannon, that one, if you understand what I mean. So this is 3 times, we can say 7 times, 6 times 5 times 4 times. Now, once we account on the grid for our problems, our arrows will count as just a number of ways we can place that. This is 1, 2, 3, 4, 5. So we're going to multiply this by 5. Sesikubonile ukuthi unjalo. 3 times 7 times 6 times 5 times 4, then times 5 again. So this gives us 12,600 dons. 12,600 different 5-letter words. So do you see what's cooking here? Yes. That is what is cooking. You know, that is what is cooking. So you will see that, okay, that very same vowel can be anywhere. It can be on the 1st position, can be on the 2nd position, can be on the 3rd position, can be on the 4th or the 5th position, because it's just a loose cannon. But within that very same thing, the restriction is that we are only choosing from the vowels. And remember, it can be any of the vowels that we are given. So very careful. This one is a hot potato. It will burn you like you, man. Man, this thing is now getting ugly. Yeah, certainly higher grade. Higher order. So yeah. This one was a bit nice-ish, isn't it? And of course, another student may want to use our stuff and say this is 3 times 7 factorial divided by. Remember, now we're going to say 7 minus, how many spots do we have there? 1, 2, 3, 4. On what looks like a factorial. So we're going to say minus 4. This is a factorial times those 5 lovely things. And you will see that yewena izawuphuma laa nto leyana ngo-3 lwana no-multiply no-7 factorial divided by 7 minus 7 minus 4, that one is also a factorial, and then we multiply it by 5. And you know what? So it all are the same things. 12,600. 12's got a 36. Difference. Aye, man. So it's papela when man. Different. 5-letter words. You see, not bad, but very good, very good. So master the technique, guys. So this question is highlighting something now. Some restrictions, if we are not told where they should be, we can just fix them loosely, then account for their movement as well. That is very important. And again, taking care to know from what are we choosing what we are choosing. Because if we are not choosing carefully, we are going to be carefully destroyed, you know. So I do hope, guys, this is nice and easy. And of course, that lovely student who is very inquisitive can say this is 3 times 7p 4 times 5. You know, almost it's going to be the same, right? So these are the options which you don't really need, but you can think about, because you never know how the memo is going to show up with the answer, especially this option right here. And you may be confused about what is happening, you know, what is this now? Because that 3 and the 5, they can be put together as 15, and it'd be like, where the hell did the 15 come from now? And what about 7 factorial divided by 7 minus 4? Say vele ipilanto. It's like kunento abangakubonisanga yona, ngoba nawe uzazi indaba zakho uzodidizela bese uyadideka ayifumana yonke lento, and ayifanelanga yenzeke lento le. Right. Now, folks, yep, this is a special piece, not like a normal P there. Right, let's do question 10, guys. Yeah, actually, guys, I'm trying to take you through these questions as slow as possible. Yeah, I know most of you are racing against time. Too bad for you, because you're not going to master this. And not mastering a topic, guys, is synonymous to just going to the exam unprepared, because there you will just depend on luck if things just come out that you studied and that you perhaps know. But if you go there mastering topics, you know that you are ready for whatever comes. Yours is just to plan your exam nicely and execute perfectly. Now, question 10 says, consider the digits 1 to 8. So there are how many in total? 8. How many 2-digit numbers? Now remember, this is numbers, not codes. So be very careful sometimes. When we say numbers, 2-digit numbers is not 01, 05, 06. Those are single digits, or they're called units. So no. So a double-digit number cannot be preceded by a 0 anywhere. What am I saying? You're lying. Let me say 0 can be put, you can put 016. That's the same as 16, you know. That's a 2-digit number. Even if you write 016, that's 2-digit. So yeah, a 2-digit number can be preceded by a 0. But remember, the 0 doesn't count as 100. It's nothing. 0 only counts after a particular digit that is not 0. Then it starts to count. Before a particular number, a natural, let me just say 0 before a natural number is insignificant. But 0 after a natural number is very much significant. It's not just significant, it's very much significant, comrades. So be very much aware of that situation. Right. Okay. if these ones may be repeated. So we are allowed to repeat. So 10.1. So we have 2 spots. Now we have 1 to 8, so it can be any one of the 8, and again we can repeat that. It could be double 1, double 2, double 3, and you name it. So that's it. This is gonna be just 8 squared, which is basically 64 different 2-digit numbers. Nice. So Bafetu, this is just basic stuff, and I like the way these questions have been structured. Good one. Kudos to the person who compiled this. That surname sounds Italian to me. So she's probably an Italian South African, Yeah, there's lots of them. Attenzione, students, meaning, hey, pay attention. Attenzione, that's Latin. Is it Latin or is it Italian? Yeah, it's whatever, man. Attenzione. Hey, ufunda lezi language, man. Maths. How many 4 digit numbers? Can you see now the whole situation has changed? How many 4-digit numbers can be formed if digits are not to be repeated? This one we want for 1, 2, 3, 4. And of course, we've got all 8 options, then 7, then 6, then 5. Pelile. So this is 8 times 7 times 6 times 5. And it is what it is. It is what it is. So again, guys, I'm sure you understand now how to use these situations when the factorial comes in and when the factorial doesn't come in. This is 1680. Nigga was 1680 different 4-digit numbers. At this point, we are happy because there's no 0 mentioned here, so we don't have to worry about nothing. So can you see, given a certain number of options, we can decide whether we are going to match the positions of whatever we want or we're not going to match it, right? But you will certainly not have a situation where you are asked more than what is available. That would be crazy. So 10.3. Of course, guys, you can use the factorial notation here if you will. Mandiniphushe kodwa ndiyanazi nina ningabantu bokuqhutywa nezingolobvane yazi ikiriva 8 factorial divides it by 8 minus how many? 1, 2, 3, 4. So that's 4 factorial. That should give us 1680 different. That's the balelani yonke lento different 4. But again, guys, ningabi ngamavila ndifuna niye kuba ngamanqenerha. Ngoba ndiyanazi ningamanqenerha nina. Digit numbers. I don't want you guys to be lazy. So I'm forcing you to do the right thing, so that you don't get confused. You see, sometimes when you repeat something in different scenarios, you even start to see its weaknesses, where it falls short and where it doesn't. But if you're just going to spot using it, you will never know when it applies and when it does not apply. So that's my intention. So be patient with me. You will live to be proud of yourself at the end of the year. But yeah, if you are not going to be patient with me, you are not going to be very proud of yourself, are you? Yes, you're not. You will always be like, I wish ndandimamele lapho and phambanela kodwa bephambana ngendlela right. Xa bendingayiqondi loo nto leyo uba indlela right yokuphambana lebeke yenza. Wena uzawucingela uba indlela erongo yokuphambana. Oku kukuphambana okuntswempu. Hayi ukuphambana okudoma. Phambana okuntsempu kabi lokho enikwenzayo la. But if I was fundisa ukwenza kanje, then andazi. Mna ke bantakwethu ndinibonisa amaqhinga okuphuma enxebeni kaxaki. amaqhinga wokuphuma kwingxubakaxaka. Are ke maleba-leba a bophelo he. Fela he nka se re ke maleba-leba a bophelo hantle-ntle. Nka re ho wena ke maleba-leba wa mathematics dipalo tsena monna. Ha batla o di tseba hantle ebile o tswelle pele ka dintho tsa hao mona. O tshwanetse hore o tsebe maleba-leba a teng. Ha o sa wa tsebe fela re tla o tsetela ke o jwetsa. Re tla o tsetela ka lethabo re tla be re tshile hakakang re tseba hore re tsetetse sehole hona moo. Yes. 10.3 says how many numbers between 3 decent and 4 4 5 4 yeah, yenaleyo. So let's see how many numbers between 3,000 and 4,000 can be formed. Now, first of all, if you study these, what are these, guys? These are 4-digit numbers. Excellent. But as you can see, what we were given has no zeros. So we're not going to pay attention to the zeros per se, but this is saying something. Now, a 4-digit number, think about it. We're going to have 1, 2, 3, 4. But there's a restriction that is not nicely communicated. You need to deduce it. You need to find it as the essence of the question. If we're saying numbers between 3,000 and 4,000 and we already know the zeros are not there, even if they were there, it would still be nice and easy. So it says there is a restriction on the beginning, the starting digit. It can only be a 3, you see. The starting digit can only be a 3 so that this number is greater than 3,000, because even if 0 was to follow, and as you can see here, there's somewhat a repetition, isn't it? Because if you look at 3,000, it's repeated. The digit is repeated there. 4,000, the zeros are repeated. So it means repeats are allowed. Bantakwethu, uyayiva ke ngokulento. Hey, mnandi nansi indaba. Qha ke ngoku into ebalulekile is that there's a restriction on the beginning. Otherwise, we are allowed to repeat. Why? Because 3,000 une repeat. 4,000 une repeat. Uyaqonda? Because remember, between 3,000 and 4,000, ukhona 3,330. Can you see all 3 baphindwe kathathu phayana? Then bese kuba no 0 phayana. If man, so enyanisweni siyawina ke ngoku. Yabona xa icinga lento, cingisise kakuhle. Hawuyinahana fela. Uyinahanisise hantle fela. Uskatata, utlashwela jwaleng wena. Utlo dikela dikoting monna. Tshwantse re o shebe mo tsamayang teng. Ska fofotheha fela bosiu mona. Re tla o tsetela. Ha re batle ha o tsetela batho. Tshwanetse re lona fela le shebe hantle mo le yang. Ebile le shebe le hore le tsamaya jwang, le etsa jwang dintho tsa lona. Le tlo tswella pele. And ha le tswella pele re tlo etsa jwang? Re tlo thaba. Tlo ba di-celebrations ka mona. Re tlo hlabela le kgoho ha re batla. Mohlomong le nku, mohlomong le pudi wa bona. Kampa kgomo, ho tlo bonahala hore na le ema hae mane. Na le yona tjhelete ebile. Ka o rekela le koloi ha re rata, wa e bona ntwe. Tshwanetse hore o nahane hantle monna ka bophelo ba hao bo tlang ka mona. Le ka moso la hao le matsohong a hao. Jwale wena o tlo tshwara dintho tse sa tsamayeng hantle fela. O nahana hore mohlomong o tlo tswella jwang pele. O ka se tswelle pele monna, o tshware dintho tse snacks. Tlo fumana ntho tse snacks. Ha etsa ntho tse grand. Tlo fumana ntho tse grand. E re go jwetse he, the secret to this ke hore ntho tse grand di thata, di nka nako, di nka motlotlo wa hao, di nka lerato la hao dinka ntho tse ngata mo wena mona. It's taxing that thing, you see. To do the good thing, it taxes you a lot. Sometimes you want to give up because it tends to be a protracted kind of a situation. Too many delays and hiccups and what. It takes your resilience to get over these kind of things, you know. Takes your motivation, takes your purpose, your vision, your desire, not just your wish, your vision. Yeah. And you know, there was once a quote in the Bible, I don't know which part or which verse. You know, I'm very bad with the verses. In fact, I never care to remember where the verse is from and what was the situation, but I know the essence though. There was once a sermon, or should I say a passage that was quoted that says in the Bible, but it was in the Old Testament, that a man's vision puts him at the table of the kings, not his wealth, not his, countenance, not his whatever you can choose, but only a man's vision puts them at the king's table, or in the table with the kings. So remember, if you've got a great vision and you act upon it, you're gonna be with the kings. You're gonna be the royalty yourself. But if you don't have a vision, you think you're gonna flash your riches, they can be finished in no time. What then is gonna be left of you? A serious joke, an embarrassment, a disaster. Right. Now let's answer the question. So we are saying the restriction is that we are going to start with a 3. How many 3s do we have between 1 and 8? Only 1 3. After that, we can repeat all the others. You get it? Yeah. So this one we can repeat. So how many numbers did we have? They were 8. So we are allowed to repeat. So this is going to be 8, 8, 8. As we could see there, that technically, essentially, those things were repeated. So we could repeat if we wanted to. But the starting part is restricted to just one digit, which is a 3. You get it? You get it. So this is basically 8 cubed. Can you see how crazy this looks? Sometimes I may just write this on the memo and it'll be like, but where did the 8 cubed come from? Ivele khona phaya, ivela khona. So 8 cubed. 8 cubed is 512 different 4-digit numbers. Right, and these ones are different. Remember, they are different, not the same. Okay, guys, so I hope this is making any sense. I hope it's making sense. So this is just saying we're starting with a 3 and the rest of those 8 digits, because we can repeat. And think of it like this: 3,330. Can you see? We've repeated the digit 3 times. You get it. You get it. And it cannot be any other number in that first position. It has to be a 3. So think about it and figure it out. So some things will need more than just, going through the motions. As you can see, it's not a very difficult question, but it's certainly a technical question. All right, guys. Yeah, now we've got a lot of questions to do. And in fact, folks, I will try now to avoid doing, all these little different techniques to handle certain questions. You just will have to do it yourself and try it out yourself. Now, I just want us to move because, we just need to try and not make this video too long and too tiring. Okay, now we're going to try and move. Of course, I'm saying I'm going to try because you know what? Sometimes it's not going to happen question 11. Question 11 says, Mr. and Mrs. Brown and their 4 children. So 4 children and 2 adults. So that's a total of 6 people. So always pay attention to totals. Line up for a photograph. Okay. In how many ways can they line up? If anyone may sit anywhere. Sometimes you can just say randomly. Right. Or just say possibilities in general. So we know that, okay, there's no way you can repeat child number 2 twice. It's only going to occupy 1 position and that's it. So this is already spelling out a factorial right there. So this is 11.1. So we know that this is going to be 6 positions. 1, 2, 3, 4, 5, 6. And it can be any one of the 6 in the first, any one of the 5 in the second, and. So this is going to be 6 factorial, which is 720 different ways. We know that these ways are going to be different. That's just the nice thing about it. Okay, easy stuff. So you can use all the other techniques, guys, I've showed you. Perhaps one more technique rather than all the others. That's it. Right. It says now, in how many ways can they line up if Mr. and Mrs. Brown must sit at an end? Can you see, no one is suggesting that Mrs. Brown is going to be on the beginning and Mr. Brown is going to be at the end. It just says they can be at an end. Right. So we know that we've got 1, 2, 3, 4, 5, 6. So we can say, well, for this end, the first part, we can just say there's 2 possibilities. It can be Mr. Brown or Mrs. Brown. And if that's the case, we know that for this end, if we put 1 down there, there'll be 1 more for the last part, right? Same thing like that. Or you can put 1, 1, and then multiply the entire thing by 2 factorial. It's up to you really how you begin. But if you just think about it and say, okay, the first position can be any one of the 2, and the last one is going to be the remaining 1 individual. Now, these kids themselves, no one said how they should sit. So this is 1, 2, 3, 4. Sorry. So these ones can sit in that manner. Are we clear? Yes, we should be clear. Ne? Yeah, that's the one, guys. That's the one. So essentially, this is going to be literally, if you look at our restrictions, it's just 2 factorial times 4 factorial. Because those kids are going to sit together. Automatically, if the parents are to sit at each end, definitely the kids are going to be next to each other, whether you like it or not. That's just going to be a 4 factorial. But the 2 factorial in this case is just that 2 and the 1 at the end, because that's 2 factorial ways. Or another student may just choose to say 1, 2, 3, 4 and say 1, 1. Okay, what am I doing? 1, 2, 3, 4, 5, 6, and then they can say 1, 1. But remember, these people can switch positions. You're going to say times 2. So that can be in 2 factorial ways. You can even say 2 factorial or just 2. And then, of course, these other kids are going to be in 4 factorial ways because they will be next to each other automatically. So if you do it this way, please compensate with the factorial. But if you start nicely, yonke into igqityiwe iphelele khonto ingaphinde yenzeke. Yayiva ke ngoku le nto. So that is 24 times 2, which is 48, ne? That's 2 factorial times 4 factorial. Yeyi wena sindiphambanela calculator. Itheni yabala ezomqalayo ngoku? Yemara 2 factorial times 4 factorial. Iyandiphambanisa. Hayi wena man. Itheni nango le way? Bona izongigezela ke ngoku. Andingaqhelwa kakubi kaloku. Hey. 48. Okay. Inoba sendibodinwa ke ngoku. ndiyazazi xa sendibhayiza sekhona ukudinwa 48 different ways. All right, guys, so you can use your NPR button for the factorial. Okay, yeah, you can do that. You can do that, but be very careful. Certain techniques can leave you hanging if you are not aware of what you are doing. The essence may be the same, but the structure and the reasoning behind it may be totally different, as I showed you. So don't be fooled by the essence of things. Rather be impressed and enticed by the very construct that underlies everything, and let everything logically follow thereafter. Right, so that is how they can sit at the ends, and the kids, they will be in 4 factorial ways in between, and that's it. So that's the answer right there for 11.2. Now 11.3 says, in how many ways can they line up if Mr. and Mrs. Brown must sit next to each other in the middle? Can you see we are putting some order to this? So this means permutation. Even the 11.2 is permutation. 11.1 is combination. All right, because combination, there is no order. Permutation, there is order. It's a sequence, you see. Yeah. Now 11.3, we're saying these two must be together in the middle. So 1, 2, 3, 4, 5, 6. This is the middle. This is the middle. So these ones can sit in 2 factorial ways in the middle. But no one said Mrs. Brown first and then Mr. Brown next. Can be either one of the two. But the kids will always have that situation. And again, this position is fixed. We can't move it. So yeah, this is going to be 4 factorial for the kids in essence, and times 2 factorial for the middle of the two. And as you can see, this doesn't change. 48 different ways. Now hold on. What does this mean? It means the instances where these two people are on either end are going to be 48. And the instances where we will find these two people in the middle is going to be in 48 again, because the total was 720. So yeah, this makes sense. It's within the range or within the domain. The domain is 0 to 720. And these numbers that we have here are somewhat saying the right things. Ne? But again, if you like, folks, you can just go on and say, this is going to be 4 times 3 times 2 times 1 times 2 times 1. That's the same as saying 4 factorial times 2 factorial, okay? Either way. So the essence is the same, but how we structured this is different. Just remember this. Don't be fooled by the outcome or the essence. The essence is this part. But you can see the essence is just as good as it is there. But the structure or the construct is totally different. And given different scenarios, this can go on very differently. So don't be fooled by some coincidences, or rather some unusual commonalities. It may leave you in tears. Now, in how many ways can they line up if Mr. and Mrs. Brown must sit next to each other anywhere? So it means these ones can be like, I man, don't care to be in a particular position. So where must we be? Now this is 11.4. So again, we've got 1, 2, 3, 4, 5, 6. So if they can sit anywhere, we can put a sort of like loose canon of the two and say, well, folks, we are not necessarily fixing you there, but we can just imagine you there. So of course, they themselves can sit in 2 factorial ways together. Then the rest of the kids are going to sit in a manner that fits this kind of description. But remember, this time, kids are not necessarily sitting together. So be very careful. So this means our friends can be in these first 2 positions, or they can be in the next 2, next 3, you know. like that. So they can be in those positions together. Yeah. So now, what is this? This is saying to you and I, this is going to be 2 factorial times 4 factorial essentially. But this 4 factorial is not suggesting that these kids are together. No. But that's the essence of what we have. And then we're going to multiply this, because these two can be anywhere. So they can be where we see them. They can be in the next. And of course, you may want to consider them as a unit at this stage to avoid unnecessary trouble. So this is 1, 2, 3, 4, 5. So we multiply this by 5. So when we account for the kids, we multiply by 5. But when we did not account for the kids, we may find ourselves perhaps talking a different scenario, right? Right. So let's see. This is going to give us, this is 24 by 2. That's 48 times 5. It gives us 240. So this, they can sit in 240 different ways. Can you see? This is again a possibility within that 720. So, yep, this is quite key. This is quite interesting as well. This is very nice. Now, the question is, guys, I like this part now. Can we say we have 1, 2, 3, 4, 5, 6, okay? And we are saying we are doing this loose canon of the 2 that may be assumed for a unit or whatever. Now, we know that these can sit in 2 factorial ways, right? 1, 2, 3, 4, 5, 6. And then we know that these dudes can be there together. They can be there. They can be there. They can be there. Now we want to say this is essentially going to be 2 factorial times. Now the arrows is 1, 2, 3, 4, 5. So we say this is 5 factorial. Are we going to get the same answer? Let's see. So 5 factorial times 2 factorial is indeed the same thing. So we do get our 240. Different ways. Okay. So as you can see, guys, the key here, why my arrows counted as a factorial here, it's because I did not account for the kids seated there. I just left those spaces blank and just decided this is where these folks can be. But the question was anchoring on the 2 sitting together anyway. But we have to consider the total positions on the grid. So this works. But remember, this technique may not work every time. Now, this is where the student needs to understand these things and decide as well why it does not work in certain instances and why it works in certain instances. So this is very, 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 very much important, if not important. Or important. You understand? It can be important, man. Yeah, you understand me now. So again, folks, we can use our permutation don't-don'ts. Where we see there's a possibility of a factorial, we can even use the factorial notations. So guys, don't be surprised when you see some crazy factorial notations that are used for that calculation. Please be aware that that thing can be done that way, all right? Okay, all right. So let's not waste time anyway, so you can explore those. I think I have pushed you hard enough on that part. If you still don't see it, then I corner. Dignamile mntwana school. 5 maths books and 3 science books. Can you see math books, science books? There's 3 versus 5. Are to be placed on a shelf. Of because the books are all different, meaning it's not the same book, not the same textbook or same edition, or perhaps for the same grade or level of study. And it says, in how many ways can the books be arranged? Can you see there's no mention of any order? So this is to say randomly. So this is 12.1. Again, we've got how many books in total? There's 3 plus 5, so there are 8 in total. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So if we're not putting any order into this, we can have all the 8 options for the first one. Remember, we cannot repeat a particular book. So it's going to be 7 options, 6, 5, 4, 3, 2, 1. So this spells out 8 factorial, which is 512, isn't it? I think so. 8 factoriale. Oh, it's 40,320. Wow. 40,320 different arrangements, or whatever this is, or different ways. Right, now remember that first part could be considered as a combination versus arrangement. No. Yes, Oskov. Yes, Oskov. Yes, Oskov. Yes, Oskov. Oskov, yes. All right. Okay. All right. So, injalo lento. So you can use your permutations button there to do your things, folks. It gives us exactly the right answer. You know. I'm thinking now. Konje bengicinga ntoni? What was I thinking? There's something I was thinking it, and now send it distracted. My lord. My lord. I must see again to anyway. Say and buy this after all. So of course, guys, we know that we can use our fancy button there, the NPR button. So that's your homework. Please do it. So 12.2 says, in how many ways can the books be arranged if the 5 math books must be together? Okay, only the 5 math books. So again, we've got how many? Don't here. 1, 2, 3, 4, 5, 6, 7, 8. Now we can assume that we're going to group these first 5 alone. But again, this is a loose cannon, right? It can move around. It's not a true fixation. So of course, the math books can be in 5 factorial ways. Don't know what I just did there. Okay, so we're saying the math books must be together, meaning next to each other. So they can sit in 5 factorial ways. We can assume that first position, so to speak. And then the other books are going to be in 3 factorial ways, but not necessarily together, because we know that this is a loose cannon. It can be there, it can be there, it can be there, it can be there. So this is going to be 5 factorial times 3 factorial times, how many arrows do we have? 1, 2, 3, 4. So we're going to say times 4, because we accounted for the other books. So let's see. This is going to be 5 factorial times 3 factorial. But since these ones were not necessarily together, then that can be arranged in 4 different ways. So we get 2880 different ways. Again, guys, you can use the different notations for the factorials, right? And you can use your NPR button also. I'm not gonna bother there, but I want to show you something different. Again, we can have 1, 2, 3, 4, 5, 6, 7, 8. And then we take our loose cannon as well. Say, fine, there's our loose cannon. Yeah. And we tell ourselves that, okay, these are the 5 math books which can sit in that manner. We know that they can sit in 5 factorial ways. And in fact, they can be there. We can think of them there, there, there. So this time we don't account for the other books because there was no restriction on them. So this is 5 factorial times 1, 2, 3, 4. We can say this is 4 factorial. Now let's see what this is. So this is going to be 5 factorial times 4 factorial. And that still gives us 2880. Different ways. Now students, I may sit back and ask you a question. Why does this thing work? Why? Why does it work? Why must it not fail if we are setting things up like this? Now, if you look at this part, if you just look at this part, remember we talk of, is it the commutative property of natural numbers? Is it commutative? I think so. Yeah, I think it's what we call commutative, or is it associative? Sometimes it's as but 3 factorial times 4 is the same as 4 times 3 factorial, isn't it? Now look at this. We've got 4 times 3 factorial is 3 times 2 times 1. Can you see this whole thing ends up becoming a 4 factorial? So technically saying 4 times 3 factorial is the same as just saying 4 factorial. So this is why this thing works. So please guys, take notice of certain things so that you can appreciate why certain things work in different ways. Okay? So why in that situation that essentially looked like just a number, this time a factorial, but if you look at it, it's the same thing as what we wrote above, because if we're to solve it mathematically, following the rules of how we do things and notations, as you can see when I just explained, it technically just clicks that, okay, all right, this is why this thing works. Okay, please guys, be aware of different options and see why they work. And sometimes see why they won't work in certain situations, because there will be some situations where those things may not necessarily work. Okay, I hope we are clear. So yeah, understand grade 8, guys. When you learn these things in grade 8, commutative, associative, distributive, wara, those things are not for fun, guys, because they will catch up with you here. When you don't understand, you will just be like, what? And yet it's all your grade 8 stuff that you took for granted. Anyway, let's not rant. Let's deal with the problems. So 12.3 says now, in how many ways can the books be arranged if the math books must be together and the science books must be together? Again, nobody decided which ones come first and last and what. So we're going to say, okay, this is 1, 2, 3, 4, 5, 6, 7, 8. So if the math books must be together, this is the situation, as well as the science books being together, this is the situation. But we know that these are both loose cannons right here. They can move around, are they not? They can move around, they can do it. So technically, we know that, okay, this is going to be 5 factorial. This is going to be 3 factorial. But since these things are not fixed, these ones can come before the maths books, or the maths books can come before this. So here we can say times 2. Either we say, well, this can be there, or it can be there. And of course, that's going to be in a way times 2, because that is going to be repeated twice. Now the question is it going to be a factorial or is it going to be just a 2? Well, that's 2 factorial ways, right? Vice versa, because if we think about it, we're just going to say maths. If you think of this as 2 positions, you can just easily say this is 1, 2 positions. So again, we've got 2 options here. It's either a math book or it's either the bunch of math books or a bunch of science books. So you can say 2 and 1. But now we know that this thing is going to multiply the 5 factorial of the math books as well as the 3 factorial of the science books. Can you see that? So that is the stuff that we need to think about. So again, it gets complex when you want to split it like that. So you just work with this in this way. So you can say this is 2 factorial. So this is indeed going to be 5 factorial times 3 factorial times 2 factorial. Now, let's see what do we get. Yo guys, so 5 factorial times 3 factorial. Then times 2 factorial, because they can switch positions like that. So this is 1440. So this is 1440 different ways. Remember, when you're doing counting principle or fundamental counting principle, it's all about different ways. Nice. So this is essentially how this thing works, guys. So very important to know that we have to account for the 2 categories. Sometimes I always taught my students like that look, if we're saying these must be together, all of them, just remember those are the categories. So if you've got 2 categories, it's going to be 2 factorial. If you've got 3 categories and those categories must be together, it's going to be 3 factorial. Njalo njalo. Okay. Yeah, one. Nice. I think we are sorted here. Okay, guys, so I'm feeling a bit tired. Question 13. Right, so guys, keep the techniques in check, please. These things tend to repeat. So these are very common questions. There's no excuse for not knowing how to do, especially after you've been shown the technique. So now let's get to question 13 and deal with it. As you can see, the cartoon there is like, what the hell? Yeah, the hell it is. Consider the word isosceles. In how many ways can you arrange the letters? Kutheni izoba ndim njena? Mayingabi ndim kaloku. Mayibe sithi man. Masike sifunde nothetha guys. Andifuni le nto ka-you, yo, iyandicaphukisa. Ewe ndiyayithetha nam kodwa ndirhalela uba sike siyiyeke man. Xa sithetha nje phangaleleyo ngesiXhosa. In English you can say when we talk in general, we need to avoid personalizing things. You know, it's not right. It's not good. It shows some weakness in one's ability to sense, some sensitive stuff around them. It means they are insensitive. So again, in how many ways can these words be arranged or the letters be arranged? Not can you. It's not me, man. It's us. All of us, or any one of us. Maybe you can say can one. See, that man is clear now that it's anybody, Indeed. I got a masiye again khona lapho. Because ayinamsebenzi loo nto leyo. But akwande ndiphambanisa njengomntu ozawuthi xa kethetha, let's say for example umntu be-presenter up. So uthetha nge-symptoms and signs of heart failure. The heart failure has your dyspnea, your swollen limbs, your coughing, your increased heart rate, irregular pulse, your low volume pulse, your distended neck veins, your swollen eyes and your palpable. Why is it mine? Why can't you just say there? Their swollen legs, swollen limbs, swollen sacrum, you name it, ascites. It could include, distended neck veins, swollen periorbiter. You name all of these things, folks, but not mentioning the word your. It irritates the shit out of me. Anyway. Right. Excuse the language, guys. Sometimes I forget I'm talking to kids, and even some well-grounded people who may be listening. Please, guys, don't take offense. I'm just a loud mouth that is just not really that significant. So don't mind my nonsense. Perhaps you can just focus on the little bit that I can contribute to good. The most that I can contribute to bad, just put it to the insignificant box, I guess. All right, folks, so we have this word isosceles. Now we count how many letters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 in total. Are there any repeated letters? Are there any repeated letters? And the answer is yes. Zeziphi is the E's. They're repeated twice. Simphaphela wena mantengo. Andihlanyisa manje. Isifana ukungidina ke manje. The S. That word. You see, that letter must not be said in a sound without qualification. Say the S letter or the letter S, because if you just say the S, wow, what are you talking about, man? Hi, man. Don't be insolent when it's not me, man. It's the language. What can I do? So siyayibona ke ngoku, guys, ukuthi U-S, okay, masingathi, yeah, the letter S is repeated 3 times. And we also see that the letter E is repeated 2 times. And the rest is not repeated. And we are like, okay, all right, okay. Now we want to know how many rearrangements can we have. But remember, the essence of counting principle is different arrangements. It's not just arrangements. This is different. This technique is based on different arrangements, not necessarily just nje. Singazihlanganisa zibe ngaphi, sizifuna zibe different. So be very careful. Njengoba bendini-introduce apha ekuqaleni, bendifuna niyazi le nto le uba inje ngoba inje. Niki batla ho le bontsha hore ntho ena e jwalo fela. Le ska iphetola he. Le ska ifetola le etse ntho tsa lona ke sa di tsebeng mona. Le tlo ntshosa ebile ke tlo ba le ya nna. Nano le tlo emela ntho tse tshosang mona. Wane lona le a re tshosa lona. Tlo re kenyetsa di-heart attacks hona tjena. Wane ha le mamele le tsa ntho tsa lona, empa re le bontshitse hore ntho ena e etswa jwang. A ke le mameleng he bana beso. Wa bona ena e bohlokwa he, ke tlo re go lona le etse ebe nota bene. Wa bona mfana ona ba re ke nota baloy. That nota is like note, please note. Nota bene. As Latin, is it Latin or is it what? I think so. I think it's Latin. Nota bene, it means note. Is it note down or something like that? Write down, but something like that. Note down. Okay, whatever, guys. A bit of English there, hicimos. As I said, guys, diferencias, not similar, not same. And there was a talk that says sameness is not oneness and oneness is not sameness. Yeah. So here when we want different arrangements, how many arrangements? We want difference. Fundamental counting principle is all about different arrangements. But sometimes you may argue and say, This one didn't specify about different or unique. So what are you talking about? Dang, now that crazy stuff is very crazy. But remember, when we arrange letters in a particular order, we are forming words. You understand? And repeating words is not that natural, is it? Yeah, it's except people who are stuttering and people are just crazy. Like some people will just repeat the word 3 times before they move on. But is it necessary? No. Naturally, there's no need. So in essence, if we've got a total number of words and 2 of them are the same, are you going to count that twice? No, not necessarily. So in essence, guys, you think of the natural situation again, because certain issues can be vague like this question. And if you don't understand the basis of this topic itself, then you will not understand what you're supposed to do, because it provides you some bit of ambiguity. Anyway, as I told you guys, the anchor of this topic is all about different arrangements. You saw me when I gave you the definition at the top. That definitely this helps us to determine a total number of different arrangements or different ways to accomplish different tasks. And we stated what this theorem says, or this principle says. It says that if there's n number of ways of performing one task and p number of ways of performing another task, the combination is going to be the product of those number of ways. This is the number of total ways of doing this together, right? I hope I said something right. Sometimes I say stupid things. Please forgive me if you heard something like that. I am not perfect. I'm certainly not a robot. Even a robot can sometimes get a glitch and then it does something it was not programmed to do. So, I mean, if that can be like that, imagine a human being. Yeah. Okay, guys, let's do. So now we've got, okay, how many letters, by the way? Remember, the words are going to be these letters. So it's going to be, there are 9. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 positions. And we've got those letters. So we've got all 9 and then 8, 7, 6, 5, 4, 3, 2, 1. Right, so this is 8 factorial ways. But remember, there are repeated letters in there. So if we have repeated letters, this is going to provide some similar words of a particular number. But now you wouldn't know this. You'll be like, yeah, then how do I correct for this? So basically, we will say, well, the number of arrangements, let's do it. We can say this implies that the number of arrangements, remember this time, guys, I will tell you, never again, different arrangements. This is the anchor of this question. But again, remember, guys, whatever your teachers tell you, arrangements is going to be 9 factorial. But because there's a repeat, we will divide this by the how many times one letter is repeated. Now you see the S letter is repeated 3 times. So we're going to say 3 factorial, because S is just S. It's not, no matter how many we have, it's just S. And then the E's are repeated 2 times, so we're going to say 2 factorial. You see that? Is there any other letter though? Please, guys, be careful when analyzing this, but it doesn't look like it. Now the different arrangements are going to be like that. And I know now you are itching to ask me the question, why the hell are you dividing by the factorial of those repeated letters? Just sit tight. I will tell you. 3 factorial times 2 factorial. So we need to correct for this, because all we want is different arrangements, right? Because if no one states clearly, we know that's the intention, because if we're using counting principle, that's the intention. So please, folks, even teachers, I beg you, emphasize the essence of what we do, so that kids, when thrown into the deep end where there's no clarity, they know what to do instead of guessing what to do. So 30,240 different, okay, that is it, different arrangements. Maybe we can even say therefore. That's it. So now you'll be like, I got a lento yakho ayenzi sense mfethu. Yenza xa kutheni sense. Now remember guys, I always told you, you need to model things so that you can understand actions. Remember we said logic is at play here, which is the study of the correct reasoning, right? Focusing on making, valid inferences, or should we say sound inferences, which will lead us to making, arguments that are a little bit valid. So now let's have a look at this situation here. Now this works, and you'll be like, nah man, I don't believe it, because it seems like it's just some cramming tool. Now I said model things. Think of the word aba. Aske starte nje aba. Isimaphambili sikahlelo 2 nina bantwana abafunda isiXhosa. Lithi isimaphambili pha sikahlelo 2 aba, since isikahlelo 1 kungu xa sithi umntu, xa siya kwesininzi ngohlelo 2 banga ngabantu, which means abantu. Ayivayo ngole nto. Kodwa umthi ayingohlelo 1. You know why? Because isininzi sakhe asingohlelo 2. Ngoba umthi xa seyimininzi sithi imithi. Ayivayo ngole nto. So ithatha la umthi yomgibisela ku-11, hlelo 11 phaya. Yes, ndikufundisa isiXhosa ke ngoku emethini khona lapho. Now, sawuthatha nje sasimaphambili aba. In English, you can just say aba, right? Let's say this is what we were given. And as you can see, we have letter A repeated twice. Now, I'm trying to show you something here, because I know with the big number of letters that repeat and stuff, it's going to be tedious. You won't finish. You will cry. You'll give up. So modeling is important to understand certain things at a deeper level. Now, let's see, how many words can we form? Let's say we want to say the A is different in that the other A has a tick in it, just to separate the two A's, but we know they are the same. So, well, we can still have ABA as it is given. It could still be AAB, where the ticked A is the second A. It could be the AAB when the ticked A is the first one. Can you see? Those are the letters that we can have that start with an A. The next ones, it can be, A that has a tick like that. The aba can be like that, the reversed order of things. It can be essentially, it can be B, A like that. It can be B, A like that. You see that A of ours that we take. So can you see that we've exhausted the possibilities now? Can you see how many arrangements do we have here? 1, 2, 3, 4, 5, 6. But do you notice that since the A's are the same anyway, nobody said they're different, but we just wanted to separate so that we can see manually. This is the same as that. This is the same as that. And this is the same as that. Can you see we're not getting different arrangements if we just use the factorial of those 3? Because remember, 3 factorial is 6, and we can see we got 6 arrangements. But of these arrangements, they are not necessarily different. Okay? Each one has 2 of its kind. Now, to correct for this, you will notice that if we say, okay, fine, we've got 3 letters here. So we're going to say 3 factorial and divide by the repeated letter as a factorial and say divided by 2 factorial. You will see that this is basically 6 divided by 2, which is 3. And if you look indeed, each one is doubled. So if we divide each one by 2, we get 1 of each. At the end, the different ones are only 3. So this is logical. It's not train smash, isn't it? So this is logic, guys. So as I always tell you, when you have big things, make it small and study the small thing. Then you can easily transfer this to the big thing, because it will always work. Because as you see this, you can increase by 1 letter. then repeats again. Of course, it's going to be a tedious process, but remember, guys, when you are studying for understanding and mastery, you need to take your time. And you need to go all the way with the tedious stuff. Because then the quick ways become like chips. You just put in the mouth and chew, and that's it. Don't even have to worry about it. So as I said, as you can see there now, when we divide by 2 factorial, because you can see 6 there, each one is doubled. So in essence, we need to take the total and divide it by 2 because each category is doubled. And if we divide by 2, we get 3 different arrangements because this is what we want. But again, guys, it will depend on what this question was trying to achieve, because someone may say, well, 6 factorial arrangements, it's okay. But remember, the A's repeat and the essence. Remember, the essence of the principle is to find different ways, not same ways. Because those things, you can see they repeat in some way. So if you've got the letter A repeated twice, you will see the words that are different. They have 2 of the same kind each. And so forth. If the letter A was tripled, you would have 3 of each repeating itself, you know. So again, you can see that as you study this, logically you start to find a way. Hence, we do what we did to answer that question. And please, guys, number 13 is your nota bene. Please remember this and remember the example I gave you. It will help a lot in making sure that you get your stuff properly. Okay, nice. I hope this is clear. If you have any questions, you can ask, but I can tell you this is how it works every time. And that small little model there is just to give you the perspective as to why this thing works. It's working because this is a logical thing. It's not a must. You can do the manual one but suffer. But if you then understand, this is good. As I said, we can argue now as to saying, but the question did not necessarily say different arrangements. In total, they're going to be 6. But as you can see, there's repeats of each of the 3 that we get. So would you say you've gotten something different if you repeat it? Not necessarily. So that's not why we want to count. We want to count differences, not count similarities. We're not interested in that. Okay, guys, I hope we are good. And of course, as I said, always think of the natural situation rather than a conditional situation. If no condition is given, you stick to the natural, because that's what is always going to be the case. But once you put a condition, then we stick with the condition because that's the intention. Okay. All right. So I hope we are clear here, guys. So please know why you do things and why they work. As you can see here, I have shown you why they work. And I hope your teachers teach you this way, or even better than this, because you cannot just know how to do things, but you don't understand why. You know, if you want to remember things, you need to know the why. It's good to know what, and it's good to know how. But if you don't know the why, you will never get anywhere. Because people can be taught what and how. But the why is not so easy to teach, because even those who teach, sometimes they don't know the why. And if you can know all these 3, you will never forget. You won't need to read again. Because the why is exactly what guides you in the what and the how, usually. Because the why part is what puts everything together. It even gives you a perspective and directives on how to go about the what and the how. But sometimes you may forget those. If you remember the why, it kind of reminds you the what and the how. Hey, masingathethi kakhulu man. Hey, qalile wena man. Qalile son. Ndicela ukuyinyanzela apha le question. Ndicela ukuyinyanzela ndiyinyokothisele apha. Ako tshetshelele kwana ke batla o ikenya kwana hona mona. Ke batla o ikenya mona. Ke batla o kalamane le kalomane, ke batla o kena hona mona ka hare ka mona. maharing wa yona. Okay, a 4-digit code is made from 0 to 6. Now how many? 6 totals, but 4 spaces to fill. So can you see there's a bit of a selection here? How many 4-digit codes can be made if the code has to be greater than 2000 and less than 3000, and that it must be even? You may not repeat digits. Can you see there's quite hectic stuff now that needs to happen here? Of course, we've got 1, 2, 3, 4 because it's a 4-digit code. And we want to start with the restrictions. Now, when we say greater than 2000 and yet less than 3, it means there's a restriction to where we can begin. And as well as the final part has to be even, it means we also have a restriction there. So in essence, guys, we've got 0 to 6. So this is 0, 1, 2, 3, 4, 5, 6 digits. We need to think about that. How many are even? Is 0, 2, 4, and 6. Ne? Good. So out of those 6, we've got 4 even digits and 3 odd digits. Okay, very important. So now we can say we can choose from 4, the last one. Right, and of course the first one, it means 2 must begin. So there's only 1, but here it's a 2. Because for us to get a number greater than 2000, it has to start with a 2. If it starts with a 2, it will always be less than 3000. Great, so we know that. And for that to be even, it's a different story. But now here we have a problem, a serious problem. You see, out of this 4, we've got 1 digit there. So that means we need to refine this one. This restriction needs to change a bit. Yes, because we can say, okay, the start must be a 2. So the 2 is out because its position is essentially there. So we can say this last one right here is going to be all the remaining 3 even digits. It can be any one of them because the 2 has to be at the start. Now that we've put down 2 out of 6, then we're going to have 4 and then 3 to choose from to get the middle digits. Okay, so this in essence is going to give us basically 1 times 4 times 3 times 3. So this is 9 by 4, which is 36. Ne? Yep, so this is going to be 36 codes. This is 36 4-digit codes. Right. So we are happy there. So this question is one of those questions which you would call a higher grade question because it has restrictions that force you a certain path without you noticing it. And you may be surprised when the memo is given. You'll just see 4 times 3 squared and you'd be like, where did that come from? You know. So if you understand and master the grid and know what to do with the restrictions, you are good to go. All right, guys, so this is cool. So we are done with that question. It wasn't too bad, but we needed to understand what we need to do. Okay. And another student may focus on this part and say that looks like a factorial. So you can apply the factorial notation for those 2 positions. And you can also use our NPR button also for that. So explore your options, guys, and see what you get. At the end of the day, if you've done it well, it's going to go well. If you've done it badly, it's gonna go badly. Right. Let's get to question 15. It says there are different shirts and 4 different pairs of trousers hanging in a cupboard. Okay, in how many ways can the clothes be hung if all the shirts must be together and all the trousers must be together. Okay, similar to the ones we've done above. 15.1, we've got a total of 11 items. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And of course, there's 7 shirts, so these are the friends. These are the friends. So this is 1, 2, 3, 4, 5, 6, 7. Okay, remember this is a loose cannon, right? It's not fixed there because nobody said the shirts must come first. We just told the shirts must be together as well as these dudes. They must be together as well. But again, these are all loss. So we know that this is going to be 7 factorial. And this is going to be 4 factorial. Okay. But we know that this can be there, it can be there, right? So there's going to be 2 factorial ways in which these things are going to work. So this is going to be 7 factorial times 4 factorial times 2 factorial. Because these are 2 categories. Yeah, man, it's easy to sting. Once you get the hang of it, you're like, send a born again. So this is 7 factorial times 4 factorial times 2, or 2 factorial, if you will. So we're getting quite a nice number there. So 241,920 different ways. Okay, easy stuff. Again, with factorials, guys, you know you can do a lot of things together there. So we've got 15.2 says, what is the probability that a shirt will hang at the beginning, see that, of the rail and a pair of trousers at the end of the rail? Whew. Interesting. Again, we've got 11 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we're saying at the beginning it must be a shirt. So we've got how many options? 7. At the end, we also want it to be a trouser. Yeah, so that's going to be out of 4. So we've got 4 options there. Then after that, we've taken 2 out. Remember, those are fixed positions. They are not mobile. They are not variable. So if we fix those 2, then in between, they can sit in any order the others. So out of 11, we've taken 2. So this is going to be 9, 8, 7, 6, 5, 4, 3, 2, 1. And those ones are going to sit like that. Okay. So this is going to be equal to 7 times 9 factorial times 4. Let's see. This is the number of ways this situation of a shirt at the beginning and a pair of trousers at the end. So this is 7 times 9 factorial times 4. This one gives us a number that is so nice. It's dangerous. So this is 10,160,640 different ways. But remember, that's not the question. Now we need to sort up the probability. I like this question again. It's a higher grade question, because there's something missing. You wouldn't remember this. We said how many are these in total? 11. That means the total without restrictions is going to be yebo. And you will know 11 factorial is bigger than this number, because if you are careless, you'll be like, wow, this number is bigger than that. So how will I get the probability? It's already going to be wrong now. So probability of event E as described in 5.2 is going to be the number of ways E can be expressed divided by the number of total outcomes when we do not have restrictions. So this is going to be 10,160,640 divided by the total is going to be 11 factorial, folks. Do not make that mistake. The random arrangement without any restriction becomes the total in that sample. Always, if not always. It's either always or always. So we take this one and divide by 11 factorial. And we get 14/55. And you can see that's a proper fraction. And that is cool for a probability. Yes, we may be wrong with the numbers if we made a mistake, but the method is good and the answer is satisfactory because we expect either a 1 or a proper fraction. So here you needed to know the total because that was the trick part of this question. You needed to know what to divide by. If you didn't know, you would be dead. So again, guys, you see, as we work through these problems, you probably are getting the hang of things. Now time is flying. Let's just move. Let's just move. Don't go. Angaqhelwa kabi. Yabona ke ngole tablet ifuna uhlanyisa. Ifuna uphambana. Question 16. Ngingakulinge nje. Intenzi igeza thina bafundini. Qhala kabi. Consider the word million. Is it million or is it million? Yeah. Gorilla. Right. Now that word, how many letters are here? 1, 2, 3, 4, 5, 6, 7. So please pay attention to the totals. Are there any repeats? The answer is yes. Sinamagama phindiweyo. U-E. Uphindwe kabini. U-L. Uphindwe kabini. Ikhona enye into ephindiweyo? Hayi. Okay, sesiready ke ngoku. We are ready. So 16.1 says, determine the number of 7-letter words. Can you see there were 7? So the 7-letter words that can be made. Now, again, when we say 7-letter words, the ones that are the same, we are not interested, okay? Sifuna angafaniyo, different ones. Kumbule, there was no specification, therefore we go the natural route. So this is going to be, if you know most, we can say the number of words. Okay, we can just jump in. Sometimes I pambana konke lokwenkwenzile. So we can say 7 factorial, right? But is what divide ngabani got 2 factorial kabani ka L. See times and got 2 factorial kabani ka I. And sithole the total number of different words. Ndicela lonto niqonde bafethu ukuthi ngalangafaniyo asiphindaphindi kwi-fundamental counting principle unless siqelelwe njalo. Kodwa you will see that the scenario will be conducive for such a situation to be considered, because the idea that whatever we do, even if we talk about repeats, it has to be such that we get different things despite the repetition. Cela siyikreme kanjalo ke. Uzobona wena khomnto zakudla. Nje nawe sekuthiwa imemo ize seyifuna uthethe enye indaba, ngeke bakudlela indlala, baza kunika imarks zakho. Uhambe uyofunda lonto oyifunayo university ne. University yoba ingcali pha. Okay, this is 1260 different 7-letter words. Again, guys, even if you were to take the others, you get it? Even if you were to take the other letters, like say in total it's going to be 7 factorial. You should remember though that the words that look the same, they count for one word. They don't count for two words, okay? Remember that when there's repeats, a repeated word is just one word. No matter how many times you repeat it, it's just going to be one word. Nice and easy, okay? Just because igama lam, if kuthethwa ngam lo ndindim, noba unganibhala kayi-3, if nguzama makhamba lo uzohlala kunguzama makhamba, umuntu omnye lo, noba unganibhala kathathu xa uthanda. Take for example a call roster. Let's say in 1 week I'm going to be on duty 3 times. But who is on duty? Me. Tim dot. So, I was with kube on call abantu abayi-3 just because ndivele kathathu. No, kube on call umuntu oyi-1 kathathu. Same with this thing. If we're talking about words, it's only one word if it is repeated 3 times because that stands for just one same word. Ne guys, I hope ndiniconvincile ke ngoku ningashake xa nibona le nto ne. Yeah. That's it. And you saw why we divide by the factorials. You saw with our analogy here. Our analogy or model, whatever you call it, revealed exactly why we do that and why it works. Right. So that's the same story right here. Now comes the next question. It says, determine the probability that the vowels will be next to each other. Okay. So again, we've got how many letters here? 7. So 1, 2, 3, 4, 5, 6, 7, right? And we can say, okay, let the vowels be the guys. How many vowels do we have? It's I, and O. Ne? So the 3 vowels payan. So we can say, okay, fine. We're going to take you, friends. But we know this is a loose canon. It's just next to each other anyway, technically. So we know that, okay, these ones can be anywhere, but they must be together. Now we know that these vowels are 3, so they can sit in 3 factorial ways, right? But there is a repeat within that factorial. Be very careful. There's a repeat of things. We're going to have to account for that. Then the rest of the words are going to come in. Because now out of 3 that we took out, we're going to be left with 4. So this is going to be 4, 3, 2, 1. Again, these ones we were not told they should be next to each other per se. So this means our combination there can be where we see it or in the next position, next position, next position, considering it as some kind of a unit. Ne? Now this is going to be equal to, I'm going to say 3 factorial, but remember, with that 3 factorial, there's a repeat. The I is repeated twice, so we're going to divide that by 2 factorial. As you saw when we had that 3-letter word, which had repeats, it's more like it. And then we're going to multiply this with the 4 factorial, which is what you see there. Now, since we accounted for these guys, these ones are going to count as just a number. So this is going to be 1, 2, 3, 4, 5. So we're going to say times 5, not 5 factorial. Okay, so let's get it done. So we've got 3 factorial over 2 factorial. We know that that answer is 3, ne? Times 4 factorial times 5, because, yeah, it's like this. So we get 360. Can you see with more restrictions, there's a decrease. So 360 different 7 letter words. Right, if the vowels are next to each other. So we can say then the probability of our event E as described in 16.2 is going to be N of E divided by N of S. So this is going to be 360 divided by, now the total is going to be 16.1. So this is going to be 1260. Right. So we divide this by 1260. It gives us 2 over 7, which is a proper fraction. And so it is appropriate for us to accept although we could be wrong in terms of the actual numbers if there was a mistake in our sorting this question. At this point, I don't care about getting the correct answer per se. I care about the correct method to the answer, right? And your job as a student then is to ensure that everything ties up nicely. That is your duty. Mine is to show you the way, but you is to walk the way. Nice and easy. So I hope, guys, we are good. I hope we understand, and I hope this is super duper clear. Now, I want to check something here because this might hurt. Let's see. Is it possible to say 1, 2, 3, 4, 5, 6, 7, right? And then we say this is our loose cannon there. And we say that this is going to be 3 factorial, right? And then we say this could be here, can be there, can be there, can be there, can be there. And we don't account for these other letters. What is that? Let's see. Now we can say this is, well, 3 factorial times 1, 2, 3, 4, 5. We say times 5 factorial, right? And as you know, that this situation right here, you should know that 5 times 4 factorial is the same as 5 factorial, isn't it? But within this 3 factorial, we saw that there was a division there by 2 factorial because of the repeat. Yikes. Injalo nakanene masibone basithola ntoni. If asithola u360 izasixelela into yoba besiphambene xa besiyisebenzisa le nto. Kodwa uba siyamthola ithetha le nto esiyithethayo nathi. Yayiva ke ngoku le nto. So guys, you see, when you know your things, you know your things, man. No one can take you down, I swear to God. So this is 360 different ways. Different, whatever, 7-letter words. Because it's all about different. 360 different. 5, no. Different 7-letter words. And then, of course, from here, we take it up to the probability part. So see, combalap. So this is what you can do as well. And you can see this works. So if your logic is right, you are not touchable. Ne? Definitely. Definitely you will not be torched. You will touch instead. Anyway, guys, so siyabangena njalo sibloko sibangenile. Now question 17. Right. Question 17 says we've got the word calculator. Is it calculate? Yeah, calculator. Wow, I said it nicely. How many words are there? I mean letters, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got a total of 10. Are there any repeated letters? Yes, the answer is yes. Bayaphindeka kabini phayana u-a baphindeke kabini nabo ola bayaliliza nabo phana bayalilizela bese kuba injabulo nje konke zonke bonke yabona ke ngoku nansi anyani la nto leyana. So there's so many bloody repeats there. That means we've got so many things to deal with. Now it says, okay, consider that word calculator, and then we deal with 17.1. It says, how many different word arrangements? Now, you see, this question is nicely clear. Now, you may want to argue these issues above that, look, when there was no specification that we're dealing with different things, then you don't have to correct by dividing and all that. Maybe. I don't know. Again, folks, what will underline and underscore all of that is for you guys to contact these people. You see, these guys, they have a number down here. You've got their WhatsApp number there. You've got their email address, you've got a specific person, you have some general queries there. You can call, you can WhatsApp, please contact them to find out what is the memo for this thing, so that even if I lied to you, then you are sitting safe. Because what I care about, guys, is to show you the method, the techniques. I don't care to get to the right answer. And of course, I'm human. I may make mistakes, but I will confidently accept those mistakes when pointed out without any other reasonability of, what do you call beyond. If you can point those things out beyond reasonable doubt, I will take it. But if there's still some doubt created in your argument, I will still retaliate, right? Even if I'm wrong, I'll retaliate. Not because I assume I'm right, but I don't just get convinced because someone else says otherwise. I need to be convinced when I find sense in what they're saying. If I don't, then I stay there in the middle zone. They lukewarm. So guys, if at all, because I'm seeing now this question is much more clearer, but remember, these vague questions are there for a reason, to see if can you picture the natural situation out of the scenario given. Would you be able to make the right judgment despite the vagueness of the background? But when it is clear, it is obvious that there is a catch as well, so that you are clear in what you do yourself, right? It's not making it easier. Once you see things clearly defined, it means there's a catch that you need to sort, right? So we want different arrangements. So we know that, okay, here we're going to have 10 factorial divided by, now we had c's repeated twice, so this is going to be 2 factorial, times we've got a's repeated twice as well, it's going to be 2 factorial, and we have the L repeated twice, that's going to be again 2 factorial. Okay, so that is going to give us the different word arrangements, which now is a more natural question to ask. But if it is not asked like this with a clear specification, you choose the natural route, because a word, no matter how many times you repeat it, you're not going to count it twice. It's all about it being that particular word, technically. You do things that are not logical, you're going to get illogical answers. So what we see now here is that we're going to have a very nice number there, 453 decent, 600 different word arrangements. So of course, guys, now this technique, I'm just jumping in because I know there's no need for me to show you the grid. This question is pretty straightforward. There's no point in wasting time. Okay, a general question that certainly is more of a repeat of what we know. There's no point. At this point, you should be comfortable. If not, go back to the grid, because the grid will sort you out, okay? Right, it says now determine the probability that the word arrangement starts and ends with the C. Can you see? Now we need the grid here. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now there's only one letter C there, right? Because even though there's 2 of them, but it counts for 1. And there's also one other letter C. So can you see we're eliminating that repetition of the letter C's. Then the others are going to just follow on into 8, 7, 6, 5, 4, 3, 2, 1. And remember, the beginning and the end are fixed, so these ones are actually not moving. Right, so this is going to be equal to 1 times 8 factorial. But now within that factorial, now remember always when we have this factorial thing, this is when we somewhat correct for things. Within that factorial, remember we eliminated just the C's as the repeated ones. So the A is still repeated. The L is still repeated. So we're going to have 2 factorial for the A, 2 factorial for the L, because the C's are eliminated. And of course, we times that by 1. And so we will get the answer, which is just 8 factorial. And now in the memo, you may find this one just written alone. And you'd be like, what happened? If you don't do the grid to understand things, you will not understand what happened. Because you'll be like, 8 factorial of velapi divided by 2 factorial of velapi times 2 factorial of sugapi nayo. Kanti ngoxa uyazi ukuthi bisuke phi yonke le ngxolo lena, awubi ne-surprise ukuthi zivele phi, because what those what you call what the people who design these things, different word arrangements. But now the question is on the probability. We know that the probability of event is going to be, please guys, take care to just write the formulae as best as you can. Doesn't have to copy anything written in the formula sheet per se, but it has to be representative of the true science. Otherwise, you lose the essence of science, you lose everything. So we're going to multiply this, divide this by the total without much restrictions, but yeah, we're wanting just the total, which is that 7.1. Again, folks, be in a position to answer this question, even when 7.2 is the only question for that kind of a scenario, because this is the typical way it would be asked. Ne? So 10080 divided by 453,600. So I get 1/45. For me, once I get something nice like this, I know I can accept the answer. Wrong or right, someone will have to find a way of being fair. Trust me. If your technique is good, it shows order and there's a pattern to it and there's some logic. Even if it's wrong sometimes. Someone might be like, come on, man. It just took a bit of fear, anxiety, time frames and all. They may just be like, man, the student is doing well, man. They understand the concept. It's just a mess in the digits and perhaps the scenario per se. But the general stuff is there, which is what we want more than the rest. So, folks, that's how you calculate the stories like that. So here again, as you can see, the C's are eliminated in a very strange way. So you're not going to write 2 for that first position, because the C, as much as they can be 5, C is just a C. In the alphabet, it counts as 1. Okay? Don't make that mistake. Again, questions like these highlight the fact that a student attends classes or not, or a student studies or not. Because if you don't study, you don't practice, you don't attend classes, because these kinds of issues can only be highlighted in a class, because alone you are likely to be confused unless your material that you use to study is very clear and elaborate. Then you may find yourself understanding. But usually you get the confidence in a class when your teacher teaches. So these are the kinds of questions that are usually done by teachers, because they know there's a lot of misconceptions. Remember, all your guidelines, when they're constructed, they literally choose, questions that have controversies as examples usually, especially the more advanced examples. And they also emphasize these for the teachers to kind of clarify for the students, because those are the areas that always remain a challenge. And this is where we're trying to drive our students towards, to solve challenging problems, because we want them to solve our problems in the world at large. Okay, all right. Guys, wrong or right, we are done there. Sometimes, I don't really care about being exactly right. I only care about knowing my way around things. because all is left after that is to perfect everything, and perfection will lead to being correct. And the only way you can be perfect is to make sure you double check, triple check, quadruple check, and pentuple check if you can. Right? Right. Which is why you would perhaps want to focus on time attack once you are good. You are comfortable with every topic. You're comfortable with all the concepts. Then you can do time attack, because what you're trying to do now is to get enough time to double check and triple check and quadruple check if you can. Because that way, even when you have made a silly mistake, you will pick it up. So again, time attack is not necessarily a bad idea. As you hear me often beating it down, it's just that it's not a necessity. You will still get your distinctions, but you may not necessarily get your target, I guess. If you wanted 100%, you probably may miss it from a mistake. Then time attack may save you that issue. But be very careful of an erratic time attack where you are just making errors everywhere. You will lose time to correct those errors, okay? So a careful approach for me uses reasonable amount of time. If you know enough and you use a careful approach, you'll be able to balance time and accuracy. That way you will have less to go and check, you will have less to correct, and you will be good to just score your marks, whatever they are, 100% or not. But again, guys, it's just a suggestion, and again, I have put this to the test and it worked, and that's what I use. And by the time I used all of these things, no one told me to do that. I just saw that is what I can do, and that's what I told my friends and peers around me they can do, and it worked for them. The reason why I'm advocating for all of this all the time is because I know I did not only have this used by me, but even by people who had no other way of doing things or who didn't know what was best to do. When they used that technique, it worked, and they got the results that they never expected. Good ones, by the way. Okay, now enough of the bragging and the talking. Question 18. Yabona guys, kusekuseni ngoku and ndifuna ulala because ndiyaphangela. Yazi andazi ndingumuntu abnormal these days. Ndinento vele ndilale ngexesha lirongo, ndivuke ngexesha lirongo. I'm no longer normal. And I can feel it. My body is not okay about it. It's not. Okay, guys. This one says 6 friends go to watch a movie. They will sit next to each other in a straight row. Fine. Temba and Lena. Is it Lena or Lena? Lena, ne? Okay. Temba and Lena have had an argument and refuse to sit next to each other. All right. Okay, how many possible how many possible sitting arrangements are there? Okay, so guys, this one is not a very easy question to answer because you can't answer this one directly. So these are the questions that we use complementary events to, so to speak. If you think about it, sitting next to each other is literally a complement of not sitting next to each other, isn't it? That happening and not happening, those are complements. So we use the idea of complementary events to get around this issue. But we're not necessarily going to do the probability here because we're not asked the probability. If it was, it would be even much easier. But again, that idea is still the same thing, is that, okay, if we cannot look at this directly, how about we look at the complement of it? If we're saying they must not sit next to each other, the complement of that is them sitting next to each other. And I think we can handle that nicely. So we're like, okay, I'm going to look at the complement of it and then sort this out. That's the idea of complementary events. This time we're looking at the arrangement, so we're not going to be doing probability, but it still uses the same principle. Right, so we're going to say, fine, how many are these guys? They are 6. So please pay attention to totals. So we've got 6 positions on our grid. 1, 2, 3, 4, 5, 6. Now, we're going to say, fine, we want to use the complement here because we cannot directly look at the actual scenario given it's too difficult. We're not going to get to the answer. Sometimes we may end up with erratic approaches. We're going to say, okay, Temba and Lena can sit in 2 factorial ways if they were to be the best of friends, and they would never be separable whenever that allows. Okay, so there they can sit, and then the others can sit here. Now the other 4 is going to be here, 2, 3, man. Don't go 4, 3, 2, 1. Okay, now we've accounted for the others, but remember the others in this case are not necessarily sitting next to each other. It means this bunch can be here, they can be there, can be there, can be there, can be there when considered as a unit. Right. So this is going to be 2 factorial times 4 factorial for all those, times the number of our arrows, 1, 2, 3, 4, 5. Okay. So let's see, what is this? So this is going to be 2 factorial times 4 factorial times 5. So this gives us 240 different sitting okay, ndiyazazi masendibhala amarhoqololo ndidinwe nyhani ngoku, kodwa ndityanga nakakuhle namhlanje, ndivele ndalala. Sitting arrangements. I think I'm deteriorating though naturally, guys. I don't understand. My writing is scaring me. Even my thinking these days is a bit flawed. Now guys, this is when Lena and Temba are next to each other. Sometimes I explain, because someone may be wondering, what are you doing? So please make it clear what you're doing, because you don't want someone to not understand you and end up mistakenly marking you incorrectly, especially when the method that is going to be on the memo is totally different from your approach. And now the person who's marking doesn't also fully understand the topic enough to see what you are doing, because some teachers are very lazy to see what the student is thinking. They only want to see what is in the memo. If they don't see it and they see something strange in you, they will kick it in the ground. But of course, those who love the subject, they'll be trying to get into your mind. Of course, also communicate your mind clearly. As you can see here, although I just started without explaining what I'm doing, but can you see my final answer is very clear what I'm doing, and so someone can understand. Okay, let's see what's next. So there are many ways in which you can present your answers in such a way that you are clear, guys, and don't be lazy to clarify your stance. Even my Lena and Temba looks horrible here. When Lena and Temba, Kane in WWE Raw. Remember when Kane was the monster? You'd be like, Lita. That's why I'm saying Lita. Hey, got guys, dala sibhanqa ne, nathi sibhanqeke futhi ngoba sizisibhanqa. Anyway, sibhanqa senjalo. Sawubhanqa lapha kwi-maths ke ngoku. Now, folks, we are done there. Remember, that was not the question, but we wanted to use our complementary events. We can say, therefore, the number of sitting arrangements where Lena and Temba are not next to each other is going to be such that, now remember, how many are these guys? 6. So the total is going to be 6 factorial minus this number of ways when they can sit next to each other, which is 240. And the answer is going to be exactly what we are looking for. See? Using complementary events. 6 factorial minus 240. So that leaves us 480 different ways. Can you see? There is our final answer. So can you see, again, this is one of those higher grade questions where you are not told what to do nicely. You have to refine yourself an approach to deal with this. Again, what was key here was knowing the total number of sitting arrangements with no restrictions. And in that total, if we remove the ways in which they can sit next to each other, those 2, then the rest that remains is when they are not going to be seated next to each other. Can you see? Those are complementary to that total of a 6 factorial. So remember that, folks. It's always like this. As you can see here, complementary events that we studied in probability are actually helping us now to deal with fundamental counting principle, provided we understand what we are dealing with and we see what is best to go for to then come to the solution that we are actually after. So this is a higher grade question, certainly one of those that make you cry. Now that we mastered how to do the grid and we mastered, different scenarios, and you can see how this works nicely, you will always be a smiling guy or girl. Right. Now, guys, if you look at that question again, could you perhaps look at the grid where we don't account for these guys like we have here? Yes, of course, we can do that, because what happens is this 5 times 4 factorial is going to be essentially a 5 factorial. So 5 factorial times 2 factorial is still going to give us 340. So you can even look at this grid like 1, 2, 3, 4, 5, 6, and say those 2 are the loose cannon that we have here. And we know that this is going to be 2 factorial when they are together, but they can be there, they can be here, they can be there, they can be there. So we can say 2 factorial times 5 factorial this time. And we know that 4 factorial times 5 factorial is still the same business. So nothing has changed. So we can. Ne? So this will still give us 240. Just to show you guys different techniques. You choose what works, but what matters is to know how it works and why it works. Then you can understand what exactly works, even without forgetting. If you just know what works and how it works, but you don't know why it works, you will always get caught pants down. Yes. All right, guys. Course is moving on nicely, but I think it's getting to the boring sections where I talk too much. What I say, guys, hang on. Now we're starting with the past exam question papers. As you can see, this is DBE 2012, Eastern Cape, DBE 2021, DBE June 2021, May, June 2024, and then some nice spices at the end, which, it's going to be quite interesting. So now let's get to these past exam question papers. I think we have learned and practiced all that we need to do. Mind you, some of these other questions, as much as they may not have been labeled as past exam question papers, they are actually past exam question papers. But others are just a creation by the creator, I suppose. So now let's handle these past exam question papers nicely now. Now, this is you getting to the groove enough to challenge yourself with the past exam type questions. Suppose the 5-digit PIN can be made up by selecting digits at random and that the digits can be repeated. Can you see that? What is the probability that such a PIN contains at least one 9? See that? Give your answer correct to 2 decimal places. Now, do you see that part that says at least? When have you heard this word? You know this one. At least usually talks about this or that or that. That's a union of some things. It's either 1 or 2 or more 9s or whatever number of 9s that we can have. Maybe 5 of them, since we are repeating here. And we know that the opposite would also work, because if we can use complementary events also in this case, this can work. So you've got some work to do, but complementary events are usually very nice to apply because they help us to really sort up some very hectic stuff. Of course, we are told to give our answer correct to 2 decimal places, already suggesting that the answer is not going to come out in the way that we know. If it is a fraction, it means the digits on the numerator are going to be maybe more than 5, and maybe the denominator also will have more than 5, so automatically the calculator will run into the decimal. I don't know, things like that, because I think for fractions, if it is more than 3 digits, the denominator, maybe 5, yeah, I think more than 5, it starts going straight to decimals. We'll see. Right, so now guys, we've got our grade 1, 2, 3, 4, 5. Ne? And remember, this question is not stating how you're going to do it. Again, this is a higher grade question. Think about it. If we can repeat, there is a situation where we're not going to consider any issue of 9 or no 9. So this is the situation when everything is just done randomly. So how many digits do we have? There are 10, so it's going to be 10, 10, 10, 10, 10. So this is going to be 10 to the exponent 5, which is it 100,000? I think so. I think 10 to the 5 is 100,000. It's just 1 and 5 zeros. 1, 2, 3, 4, 5. Yeah, it's 100,000. 10 to the 5. Again, guys, know these things, that if you've got a whole number followed by 0 and you're raising it to some exponent, the zeros are going to match the exponent. Okay? I hope we are clear there. Okay, maybe I'm wrong. Let's see. 20 to the exponent 5. What is it? Yeah, this is 100 squared. So let's say 20 to the exponent 5. Dig up happy up. You see, it's a different story. Now, let's say if it is a 1. Okay. Before I start lying, because sometimes it's easy to lie because something seems to work. If you've got a 1 and however many zeros you have and you're raising that to some particular exponent, means the zeros are going to match the exponent and the 1 will always be present. But if it is not a 1, it's going to be a different story, okay? Don't make the mistake. But even if it's a different story, how many zeros would you have there? Let's see. Because my argument about the zeros would still probably work. Let's say 20 to the exponent 5. You see, we still get 5 zeros. You see, we still get 5 zeros, even though the number is becoming now 32. Right? So this is basically 3.2 million, right? Or 3,200,000. So essentially, you will see that even though the 32 is different now, but the zeros still match the exponent. Because if a number was followed by however many zeros we have and we are raising it to some exponent, essentially the zeros are going to be as many as that exponent we see. Then the other digits are going to just come out down. Okay, nice and easy. So guys, learn these things. Again, you learn these by observation or through observation. So this is exactly however many we can get if we're repeating the digits and we are not necessarily choosing what is what and what is what. So we can say different 5-digit pin or pins. Now that is the first thing. This is now the general thing, the total, the things that we're going to divide by. But now here comes the issue. We want to have at least 1 9. We want to have at least 1 9. Now this is going to be a problem, you see. This is going to be quite a nightmare. Are we not going to have a problem? We are going to have a problem. Because now if we're going to say at least 1 9, we're not going to be able to do this. It's going to hurt. But if we say there is no 9 at all, that we can handle, right? We can handle a situation where there is no 9 at all. And a pin can start with any other number whatsoever. So we can say, well, we can consider ourselves a situation and say also, we can say a pin with no 9 in it. Right? This is going to be again 1, 2, 3, 4, 5, 6. No, how many? There's 5, sorry. So 1, 2, 3, 4, 5. Okay, that's it. Now, out of the 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're saying, thank you very much, comrade. So how many choices are we going to choose from? 9 choices out of 10. So 1, 2, 3, 4, 5, 6, 7, 8. Mark 1, 2, 3, 4. Oh, 4 is missing. Yes. Bonak. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are saying, yay, Puma wena. So we've got how many choices to choose from? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can have these ones repeating. And this is nothing but 9 to the exponent 5. Now let's do this one. So this is 9 to the exponent 5. Gives us a 59,049. Different pins. Now remember, now we want the ones that have at least 1. Now those ones that have at least 1, they're going to be the complement of this. At this point, we don't really care. We can say therefore the probability of event as described is going to be the number of these things divided by the total number of outcomes, right? Now this one is going to be essentially the total, which is the 100 scored, minus the 59,049, and all of that divided by, again, the 100 scored. That would give us the probability using the concept of complementary events, because that's the best way we can handle situations here. Otherwise, it gets a little silly. So can you see this one goes straight to decimals? It's going to be 0, comma. Now we were told to 2 decimal places is going to be comma 41. That's the answer there. Again, it's a proper fraction. We are happy. Okay. Yeah, this is good. This is good. So as you can see, we would have had a lot of digits, more than 5. 1, 2, 3, 4, 5, 6. As a result, it means whatever we simplified was going to have more decimals, more digits in the denominator, maybe in the numerator as well. So this would essentially, lead us to just a very bad fraction. Hence, it just jumps to the decimal straight up. Okay. Again, guys, be aware of these issues, because I tell you, sometimes these become exam points. These become the examination points, so you don't want to miss these. Alright, so that was an easy question once we know how to use our complementary events and stuff. As you can see, all these questions are put next to each other somewhat so that you can learn to apply the same technique you just appreciated above. I hope we are clear, guys. Again, we can get it wrong by just making a mistake somewhere, but the technique is clear. The approach is clear. All right, let's get to the Eastern Cape 2021. I've done actually this question paper on my channel. For those who are friends with my channel and who are subscribers, you would know that, okay, this thing is there. So yeah, this is more of a repeat. Again, it helps to emphasize a point. So let's go to it. In a certain province, vehicle number plates have the following format: triple dondons and triple dondons. These are 3 letters followed by 3 digits, where this A represents the letter of the alphabet and the hashtag is for the digits from 0 to 9. See, this is very clear. Now it says for each number plate that is assigned to a vehicle, the following conditions must be met. All letters of the alphabet except ego can be used, and no letter can be repeated. Can you see now? We can use all except 3. So we've got 26 minus 3. This leaves us 23 letters to choose from. Now it says no number plate code can start with a vowel, right? Now how many vowels are out already? E and O are the 2. So we're remaining with 3. So out of these 23 letters, we have 3 vowels in there. So we can say 23 minus the 3 vowels because we don't want them to feature at the start. So it means we can only start from 20 options. Can you see? This whole thing is a disaster. So the starting letter here is going to be from the 20, while we can use 23 in essence. These vowels are included, but they cannot be at the beginning. So the beginning is a different scenario. So again, all digits can be used and each digit can be repeated. Can you see? This is good. So this is one of those crazy questions, which in itself, you can easily say this is a higher grade question altogether because it's going to be horrible. And it says how many vehicle number plates can be assigned. How many vehicles can be assigned a number plate code according to this system? Okay. So we've got 20.1. Now 20.1 says how many? Now we've got 3 letters, 1, 2, 3, and then 3 digits, 1, 2, 3. Great. So we will start with the letters. Now we know that at the start, how many options do we have? Only 20. Why? Because we were told a vowel cannot start. So we could only use 23 letters here. Out of the 23, only 20 can start because we don't want a vowel at the beginning. So that is what we do. But now for the remaining positions of these issues here, it is going to be, now out of 20, we take 1. Remember, the letters cannot repeat. Once we take 1, we remain with 19. Now this 19, we're going to bring back that 3. So again, 19 plus 3 is going to be 22. So we're going to have 22 here. And then once you put down those, it's going to be 21. Can you see what is happening here? So all we did here is that we wanted to start with the beginning. The beginning cannot have a vowel and we can only choose 23. So 23 minus 3 is 20. Now once we put down one of the 20, we remain with 19. Then we add back the 3 vowels we took out. Then 19 plus 3 gives us 22. And then that's why we have 22 now for that letter. And then we can also put down 1, we get 21. So we are done with the letters. Now we go to the digits. Digits, again, we can use any of the 9. So, any of the 10. So these ones, since we can repeat, this is what we have. So this is going to be equal to 20 times 22 times 21. Right. Times 10 cubed. Again, guys, you can use our factorial notations or the permutations button if you can see the pattern here. It is honestly up to you. I'm not going to go to that in the interest of time. Sometimes, yeah, it gets overwhelming. So what we have here is 9,240 scored, right? 924 and 4 zeros. So this is number plates, or maybe cars, we can say, because we're told how many vehicles. So we can say vehicles. Nice. Always answer the question. We're using number plates as a surrogate for the vehicles here. So I hope you guys can see and appreciate that calculation. It's really nice. It's really easy, not complicated, but make sure everything is working out properly, or else it's going to hurt badly. Nice, 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 nice. Is everything all right? Yeah, I think everything is good, guys. So I'm a bit tired, so excuse me, guys, for being slow. Now it says calculate the probability that a number plate code chosen from the number plate in 20.1 at random contains only one vowel and ends with an even digit. So this is again a crazy, crazy, crazy situation. So obviously the first part is the total that we can get, but this time we're going to a specific type of plate numbers. Okay, right. So we're gonna go on and say 1, 2, 3, 4, 5, 6. Of course, the first three is the letters. Again, remember we were told that it cannot start with a vowel. So basically we have 20 options for the start. But now these remaining positions are a bit of a situation for the letters because we want only one vowel. Now let's just assume our vowel is here. If our vowel is there, what can we say? How many vowels are we able to choose from? Only 3 out of 5 because the other 2 were already eliminated. So we know that it's going to be 3 from 3 vowels. But now since we are putting only one, we're not going to add the vowels back. Right, right. So we're going to say, fine, we had a situation here that we can only start with 20 this time when the vowels are out. Then if we put down that, we've got 19. Of the 19, we can only choose one vowel. So we're going to have a vowel from the other 3 that we eliminated, this 3 there. So that is the 3 that we have there. And then any of the other 19 remaining letters because we don't want a vowel after that. So we only choose a vowel once and then we have all the other 19. Okay? Right. I hope this is clear, guys. So this is a crazy question. And then, of course, we were told that the end must be an even digit. So of the even digits, we've got 0, 2, 4, 6, 8. So there's 5 of them. So we're going to put 5 in there. And once we put down 1, what are we going to do? Remember, we can repeat. So we got all the 10. Nice and easy. So this is how we can sort up our grid. So as you can see, the start, we need to compensate for that. And then the following digits, we can choose only one vowel. So that means we have 3 options because there's only 3 that we were allowed to use. But after that, we cannot use any other vowel. So it means we only have the choice of the other 19 remaining letters from the 20 that we started with. Very crazy question. Then we go on and say, okay, for the ending, we only have 5 of the vowels. Of the even digits. So we can choose any one of those. And then for the other option, there's all of the 10 put together. So this is it, guys. So we can calculate the number of ways in which we can get this. Again, folks, at this point, I'm not interested in trying. Oh, wait a minute. Wait. Remember, the vowel can be here. It can be there. So we need to account for that because the vowels can switch positions with the 19 other letters. So the one can come before the other. So that would spell out 2 factorial. So good. So this is going to be 20 times 3 times 19 times, we can say 2 factorial right here. Then times 10 squared. This is 10 times 10 times 5. Okay. So the 2 factorial is because the 3 and the 19 options can switch positions nicely. So we've got 20 times 3 times 19 times 2 times 10 squared times 5. So this gives us 114,000. So this is 1,140,000. Okay, that's good. So that is basically different number plates. We can say different number plates. Okay. So now we are looking for the probability. So we can say, well, then the probability of event as described is going to be the number of ways that event can occur divided by the total outcomes. So this is going to be 114,000 divided by the total at the top. It's 9240,000. Right. So this one we divide by 924,1234. All right, we get 19 over 154. Okay. So yeah, that's the one, guys. So yeah, some questions can tax you a bit, Yeah, some questions can tax you a bit. So this one is one of those silly questions. But at the end of the day, if you know what to do, you get it done. Let me just go and drink some water, please. All right, guys. Oh, yeah, send yourself. I want Anzolala ni. I want the Apangela. Maybe the best thing, Banvelen Galali. Anyway, guys, so that's it. That's it for that. All right. Yeah, it's one of those crazy questions, but again, it's a second round for those who watched my channel. There's lots of videos there, guys, full papers, so utilize them, please, for your own good. Because I can see you guys have slowed down on using things that will help you. You are busy using things that are not going to help you. Stop it. Even if your teachers force you to attend a particular class, and if you realize that class is useless, and you have some tutor online who teaches you better, yes, you need to be nice, be creative. Instead of just saying you're not going to attend because it's useless, you will make those teachers be angry at you and then they will sink you. What you need is to just say, you are a person who is on some medication that you need to take at a particular time, and whatever that class is going to clash with that time, and you cannot concentrate at that time, they will excuse you, and then you go and do what's right. But again, don't just be careless about this. If your classes are beneficial, stick to them. If everything is beneficial on both sides, then you decide which one you're going to prioritize and which one is going to come second. But whatever you choose, just remember, the consequences are going to be the results that you get. And those results are your own doing. You can blame whoever you want, but you accepted it yourself. Remember that. Now, 21 says, a 3-digit number. Do you see this? A 3-digit number. Now be very careful. A number is a different story. Now, a 3-digit number cannot start with a 0, say 025, because this is just 25. Okay? So a 3-digit number cannot start with a 0. So this is already suggesting something. Not a code. A code is a different story. We can. A PIN, we can. But a number, no. Right. A 3-digit number is made up by using 3 randomly selected digits from 0 to 9. Of course, we know there are 10 in total. But the ones that can start, they are only 9. Because 0 cannot begin a 3-digit number. Okay, no digit may be repeated. Nice. So this was June 2021. So it says determine the total number of possible 3-digit numbers greater than 100 that can be formed. See, nice questions again. So 21.1. We want 3 digits. 1, 2, 3. We know that 0 cannot begin. So out of 10, we can only choose 9. Then after that, 0 comes in. So 9 comes in also again. Because remember, out of 9, we would be down to 8 plus 0, which is 1. So this goes back to 9. Hence, we have 9 there. Then we can have 8 because we cannot repeat digits. But is that correct? Not quite. Because we were told what this digit should be. It starts with a 1. Because for it to be greater than 100, it has to start with a 1. So this needs modification now. So we're going to say, okay, fine, 1, 2, 3. Now, if we're saying this has to be greater than 100, it means we are fixing the start here. We're saying the start must be a 1 because a 3-digit number that starts with a 1 is definitely going to be greater than 100. Right, so we can only choose 1, 1. And then after that, remember, we can choose now any of the other surviving 9 digits, and then there will be 8. So this is essentially what is cooking here. So the start was fixed in a nice way. To say this must be greater than 100 means the start should be a 1. Right, so this is basically 1 times 9 times 8. 9 times 8 in Banganin. 72, ne? 9 times 8, yebo. So we will have 72 3-digit numbers. 3. Okay. So not a very difficult thing to think about as long as you remember. As you can see, I quickly ran into some trouble, but at the same time, it was quick and easy to fix oneself. Now the second question says 21.2. Determine the total number of possible 3-digit numbers again, both even and greater than 600. See now, more, and more don'ts. So we have 1, 2, 3. Okay, so for it to be greater than 6, 100, it has to start with a 6. There's only one 6, right? Right. And then the end must be an even number. Now, out of the even ones, we've got 0, 2, 4, 6, and 8. So we already took out 6. So now we only have how many options? 1, 2, 3, 1, 2, 3, 4. So we only have 4 options for that. Right. Right. Now, remember, everything counts as one option, 4 options and stuff like that. Now, in between, we've taken down 2 digits out of 10. So the remaining ones are going to be 8. So this is going to be 1 times 8 times 4. So this is basically going to be 32. 32 3-digit numbers. Okay. Sekudinekile ke senibhala kakubi kangaka guys. Hayi futhi andizoyilungisa. Yes, sesindiniwe manje. I am really tired. So this is 1 times 8 times 4, which gives us 32 3-digit numbers. Okay, that's much better. This one we can fix now, because I'm gonna publish this in the description, guys, so be on the lookout. 1 times 9 times 8, this is gonna be just 72 3-digit numbers. Okay, that's not bad. So that's it, guys. So this is cool, so sometimes these ones you can easily say maybe standard grade questions, because there's nothing really hard here, unless of course, guys, I'm taking this too light, and it happens sometimes. You just overlook certain things when there's some silliness, but don't overthink the situation either, yeah. Yeah, man. You're doing all the way. Đang bộ. So yeah. I don't know, man, guys. This thing looks simple though. 10 important. And I don't remember doing this memorandum, did I? I'm kind of feeling like, yay, when I'm telling ndiyayibhayiza yonke le nto. Ingathi ndiyayibhayiza, man. Let me see. Look, guys, if we say 0 cannot begin, I'm thinking about this thing now. If 0 cannot begin, and we've got 0, 1, 2, 3, 4, 5, 1, 2, 3, guys, 4, 5, 6, 7, 8, 9. And we're saying 0 cannot be any one of these numbers starting. It's certainly going to give us a number greater than 100, ne? So I don't think we need to certainly say 1 must be the start, because we're not given a range that this is greater than 100, less than 200. So this is a big mistake, eh? Damn it, man. Damn it, man. Yabona ke nansi into engicaphukisa ngalento. Lento yapopanisa sometimes. If we have fresh. Here it is 1, 2, 3. So this means, since 0 cannot begin, any one of the 9. And then once we put the 0 back, because 0 comes in here, would have had 10, right? And then 0 is out, 9, and then 8, and then we add, sorry, the 0, so it becomes 9 again. And then 8. So this is 9 times 9 times 8. Yeah, hey guys, please check the memo. At least there's a reference here. Go and check that memo. I don't really remember doing this question, so oops. Now I don't have, now I'm getting it raw. Is the raw stuff, ne? Okay, calculator. Oh, my tablet is also running out of power now. Damn it, man. So I'm getting 648. Okay, 648. 3 digit. Okay, masibhale kahle. Kuyafana noba ningakhalala sekubhedile manje. So this is 3 digit numbers. Right. I know these things cannot be standard grade. It has to be a higher grade. I think the second opinion is correct, guys. But yeah, do double check, folks, by looking for this memo. Sometimes my confidence levels, bandla. Sekubheda kakhulu. Sekuyabhulwa kuyembeswa lapho. Ziyanikhalela. Okay, must call it send because my tablet is losing power anyway. So this means we need to think about this again. I'm not sure if what I did is fair, because why should I fix it to 1? A number greater than 600 can also start with a 7. It can also start with an 8. It can start with a 9. That would still be a number greater than, you see. So that's the thing. So yeah, I think I'm careless here. Let's fix this issue. Right. So guys, you can see nani it's time to stop and just rethink what you've done and come back and plan your thing. But check this one. I'm not so sure anymore. Now, all I know is that if we're saying the number must be greater than 6, it means it can start with the 6 and all these other numbers. So this means 6, 7, 8, 9 are the possibilities. But if this is going to be even, and we are not repeating digits, are we? Yeah, digits may not be repeated. So this is going to be a bit hectic. Let's see, it's going to be 1, 2, 3. Now, we've got a few possibilities. The problem is that for this to be even, we know that actually the start can also be even, meaning 6 and 8 can start. So let's say the start is even. If the start is to be even, we've got how many digits? If the start is to be even, meaning it's either a 6 or it's either it's going to be either a 6 or 8 when we say the start must be even. So we have got 2 options here. And then for the end, once we put down 1, so we've got 2 options here, 8 or 6. That's why we're saying 2, because those ones will give us a number greater than 600. But then we can bring back all the other we can bring back all the other digits in the picture, because now we are just building this number nicely. So look, what we want now is to focus on the end. Remember the beginning, we have sorted it now. We've got 2 options for the beginning. Now, how many options do we have for the end? Right. Remember, we've put 1. Now, the even digits are how many? They are 5. Now, if you've put down 1, because I mean 0 comes back now. They are 5, and then we've put down 1, which is a 6. Okay, ngathi izonditricka le nto, ithe ngathi ifuna undihlanyisa manje. Yes. Okay, let's do it this way. Khona into engathi izoyibhuda la le question ifuna ukundibhayizisa kakhulu manje. Let's say the start is even, right? I think this is the best thing to do. But this is our spices. We've got 1, 2, 3. So let's say it's a 6, right? If this is a 6, we're starting with a 6, or should I say, okay, we've got 2. We've got 2 of them, right? It's gonna be a 6 or an 8. So we are fixing the beginning. This is fixed. It's an even number at the beginning. Now, of the 2 even numbers that will give us a number greater than 600 is going to be 6 and 8. Then, once we put down 1 even number, how many have we left? 0 comes in, so it's going to be 0, 2, and 4, and 8. If we say, for example, 6 was there, so there's going to be 4 left. Now, again, this is fixed because we were told this should be even. Now, in between, if we put down 2 numbers already, so out of 10, we will have only 8 left, isn't it? So this means we're going to have 2 times 8 times 4. So let's see. Now remember, the start is even. I would say the starting digit is even. Let's just put it nicely like that. Is even. Space young shy. Okay, must move it up. Okay, I get young papel. Now 8 by 4, that is 32, by 2, that's 64. 3-digit numbers. Okay, or what else could we have? We could have an odd beginning, or the starting, we can say starting digit is odd, because those odd numbers themselves can give us something. So we've got 1, 2, 3. So of the odd numbers that will be greater than 600 is going to be 7 and 9. So there's 2 of them. But we said the end must be even. Now, if this is to be even, we've got all 5 even digits that we can put at the end. Now, in between, we're going to have 8. So this is going to be equal to 2 times 8 times 5. Which is going to be 2 times 8 times 5. This is going to give us 80. 83-digit numbers. Alright, so guys, at the end of the day, we will take these, because remember in maths, this friend is saying we are adding. So we're going to take that and take this and add them up to the total number of the situations, because I think the trick was just to get that sorted. So all we're going to do now, we're going to say, therefore, the number of 3-digit, therefore the number of 3-digit numbers. Wow. We can say therefore the total number of 3-digit numbers. Okay, Masicho Angel. Therefore, let's just say therefore the total is going to be 80 plus 64. which when we add 180 plus 64, it's 144. So this is going to be 144, 3-digit. Yo, hi guys, ingathi iyandiweka ngokule nto. 3-digit numbers. Hayi. Seyindenza ndibe nokubilayela, but I'm feeling confident now. Because I think what we did was rather careless at the beginning. So this question is never really that easy. With restrictions, it's not that simple. So maybe I'm overthinking it. Maybe I'm not. I don't know, guys. Sometimes I found myself doing those kinds of things. In the exam, I find myself rubbing and tearing the pages and stuff. But it happens, guys. So think about what you're doing. Now this question is just deflating me now, you know. Okay, I know what Valiant buys this, but I'm the question is on buys this. I since there are very ezininzi perfect. Yeah. Diniwe manje. Athi ngigalele futhi into esiselwayo. Igalele kamuntu. Mina nosela amanzi walapha, amanzi amhlophe la ngiyabona. Agqiba kwa purifier, yabona into ezinjalo. And I'm doing the wrong thing of selling juice. I had to sell juice and go 5 exchange. Out of Nenlale. Let me finish up quickly. So guys, I think this one is much better. Because this situation is key sometimes when the restrictions clash. For example, we were told that this should be an even number and it has to be greater than 600. We know that it can start with a 6, it can start with a 7, it can start with an 8 and a 9, you know. So that could be the start right there. And if that's the case, it means we need to consider when an even number is at the beginning, it affects the number of options for the end. And when it is an odd number, it does not, okay? So I think, yeah, this is one of those questions that are low-key killers, especially this one. This one is truly one with an asterisk or even 2, because you wouldn't think about this split, would you? As you could see, it looked so easy to just go in, and yet our planning, we were just looking at things wrongly. But you see what, now I'm even starting to wonder if what we did. But this one was easy because we were given a range, so the start was fixed. I think this is what misled us. We didn't do any other question like that. So please watch out for this question as well. If ever we did it well, just double check. But I'm seeing we just fell into the trap here. Okay, again guys, it's nice. It's a question paper that was written recently. Or in the recent past, you can say, so you can go and look it up. Please double check, correct me where you see some mistakes. As I said, I'm not the person who has all the answers, but I just give my 2 cents, if you call it that. But again, this is just me trying to be modest. I'm an arrogant freak, and I will remain as such, unfortunately. If I can become anything else, I would be a weak individual, unfortunately. My arrogance is not so bad, though. It doesn't stink, I know. Okay, maybe it does at some point. Sometimes I become a little more than I'm supposed to be. Sometimes I'm a little bit ahead of myself and stuff, maybe assuming and all. But at times I'm just, easy. Or at least I think so. Right, 22 guys. You're high, but when this Belanin as this way, you're high, yeah, but nah, yeah. Mandigenzi wanjalo these questions. Now, this is May, June 2024. Again, guys, you can go look up the memo if I mess up anything. Now, 7 guitar players. I think I've done this paper though. 7 guitar players, each with a different name, participate in a concert. Right. Now, how many are these folks? 7. Again, guys, pay attention to totals. And obviously, this is a natural situation. Can we repeat a guitar player? If they are to be standing next to each other, we can't. But in terms of playing on the stage, we can repeat. Yeah, think about those things. Okay, in how many different ways can the names of the guitar players be listed one below the other in the program? Again, there's no specification that they're doing this in alphabetical order or males first, females, or whatever. So this is a random thing. So we can think of this one below the other as just a long stretch of them sitting next to each other. So we can say 22.1. We've got 1, 2, 3, 4, 5, 6, 7. So you know, guys, great stuff. It's gonna be 7, 6, 5, 4, 3, 2, 1. So this spells out 7 factorial. So we know 7 factorial is it means got 7 factorial masibone 50 40. Yes, this is 50 40 different ways. Right, that one straightforward standard grade question. 22.2 says after the performance, the guitar players wait backstage. Right, there is a bench with only room for 4. Can you see we're dealing with selections here now? We've got more options, less spots. What will be the probability that the 4 guitar players will be sitting in alphabetical order from left to right? Oh, by the way, we're told these guys have different names. Okay, each with a different name. So that's very important. But I was like, okay, the repetition is going to be an issue as well here. Right, so guys, we've got 4 spots, 1, 2, 3, 4. So of course, we've got all 7 options, 6, 5, and 4. And that's it. Now it says what? Okay, this is how they would sit these guys. I'm thinking now. Yeah, this question is one of those low-key killer kind of questions, because we need to consider the total of ways and then the specific way that we're being told. So in general, this is how they would sit in those 4 seats from left to right. But we've got to consider when they are now placed in alphabetical order. So this is going to be 7 times 6 times 5 times 4. Let's get the calculator. So 7 times 6 times 5 times 4. So this gives us 840. 840 different ways. Now remember, this is the random stuff. Random. This is when we are not necessarily putting them in alphabetical order, because this question can trick us to our death, because one would want to gravitate to using that total for the probability. But unfortunately, this one is a different scenario than the one above, so we need to be careful. So the total here is specific to this question. So we can say also, we know that in alphabetical order, this is going to be 1, 2, 3, 4. Now those who manage to sit, obviously, there's only going to be one of each kind, because everyone has a different name. So we only have a single option for each position, meaning one with the first alphabet and the rest. So this is literally just going to give us 1. So there's only one way they can sit in alphabetical order. But this one is a random sitting when we don't really put this. You can say then the probability of event is going to be the number of ways that event occurs divided by the number of outcomes in our sample. So this is 1 divided by 840. And that's it. Okay, so yeah, that one was nice, but you needed to get the total. So we needed to find that total. Otherwise, making a mistake of using the total in 22.1 would kill us softly. Okay. So 22.3 says, during the performance, the 7 guitar players sit in a line. Okay, they sit in a line on stage. 4 guitar players are female and 3 are male. Now, in how many different ways can they be seated if the males may not sit next to each other? Again, do you see that question that we were dealing with up there? So this is again a higher grade question. That is also. All right, so these guys can sit. What is this question? Okay, in how many different ways can they be seated if males may not sit next to each other? Okay, fine. So what we can have here is that we've got 7 positions. 1, 2, 3, 4, 5, 6, 7. Now, usually, to say not, that would be a complement of when they actually sit to each other. So we can utilize our complementary events technique here. Okay, cool. We handle our business nicely there. So we can say, well, how about they sit next to each other? So there's going to be 3 factorial ways that they can do it. And then we can have the other ladies here, which is going to be 4, 3, 2, 1, right? Right. But we were not told that those should be next to each other. So this means our unit can be there, can be there, it can be there, it can be there. So this is saying we're going to have 3 factorial times 4 factorial times 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's see. This is when the boys are going to be next to each other. So this is 3 factorial times 4 factorial times 5. So this gives us 720. 720 different ways. This is when the boys are next to each other. All right. We can say boys next to each other. Can you see? So we are explaining what we are doing. Remember, be in a conversation with your marker, because your marker may lose you and then end up victimizing you unnecessarily so. Right, so we need to use the complement. Now remember, if we're saying these next to each other, what was the total ways in which these guys can sit, by the way? How many are they in general? They are 7, so we are expecting something like 7 factorial, right? Which is exactly what we got above. So we know that if we're using complements, we're going to use the general situation versus the specific situation. So we can say, therefore, number of ways with boys not next to each other is such that we will have 7 factorial minus 720, which is going to give us what we want. So 7 factorial, which was the total random sitting of all 7, minus when the boys are seated next to each other, which is 720. It leaves us 4,320. Okay, different ways. Okay. Right, guys. Hey, kuyasa phandle angikakalali. All right. So siyawina kancane kancane. But yeah, I'm losing my focus now and my enthusiasm. I don't know. Yeah, but anyway, guys, angikwazi ukubukela nje mahala. Sometimes funeka nibhayize vele nizokwazi ukuthi nani ni-engage, ne? But I think I wrote this as best as I can, so I'll publish it. But of course, I will try to see, even though I may publish the video before I publish these documents in the description, maybe after 2 or 3 days, check the description for these documents. I will try to refine how I wrote things, so that it's nice and clear. Because yeah, at times, I just don't know what I write, I don't know. All right, folks, so I think using complementary events in a way, this was the technique to get things done. So please, this is very key. All right. And of course, guys, you can see how these things work. You can see all the different options. So I'm not going to explore anything now. I'm tired. Okay, let's do question 23. Of course, my students, those who attended classes, we did all of this. Okay, most of these questions. Now I'm doing all of them so that they can see everything nicely. But even for those who are seeing this for the first time, I'm sure you will benefit. Yay, my tablet is losing power. Let me move. Let me move to the power. Let me try to finish this as fast as possible. If I can get just an hour. Kovanele ukuthi ngikhe ndathi ukuquma ubuthongo because bengikhe ndalala emini bezikhe zandikhalela Sunday. Aze zandibuyela ngecawe ikhole yami indiwekile guys andidlalisanga. Right, consider the letters, whatever that is. If all 5 letters are used and all possible arrangements can be formed, are placed in alphabetical order. In which position is the word maths? Wow. All right, so this is a good question. We've answered this in the group, so let's do it again. Now, folks, unfortunately, I couldn't find a fancier way of doing this. Maybe somebody may have a better idea on this, but I'm going to show you my raw and very mechanistic approach to this. Right. So we've got 5 letters, right? 1, 2, 3, 4, 5. Of course, we're going to have 5 factorial ways in which we can have this sorted. Now, you know what I was thinking here? In fact, what I proposed to the group was to say, look, we can think about a situation as to which letters are going to start here. A, right? So a letter can start with the letter A and everything else, right? Yeah, we can have A and then all the others. A, 1, 2, 3, 4. 1, 2, 3, 4, 5, sorry. And the next one to start here is going to be A, B, C, D, E, F, G, H. It's going to be H at the beginning. 1, 2, 3, 4, 5. Right, and then M is the next one. 1, 2, 3, 4, 5. Can you see? So if we can calculate how many those are, we will certainly have a position for the M ones, isn't it? Yes. So to answer this question, we can say starting. Okay, we can just say words that start with A are going to be 1, 2, 3, 4, 5. There's only one A there. And then the rest are going to be in 4 factorial ways, right? If we fix the start, the rest is going to be 4 factorial ways, isn't it? So this is basically 1 times 4 factorial. So this is basically 24 different words, right? That is words that start with A. So there's 24 of them. And then we can say also words that start with H are going to be this way. 1, 2, 3, 4, 5. There's only one H, and the others are going to come in 4 factorial ways. Right, so this is again 4 factorial essentially, which is 24 different words. Now we can see that these two is 24 plus 24, it gives us 48. So these ones are going to occupy the first 48 positions. Now comes the ones with the letter M. Now with this one, what I decided we would do, would say, well, the one that starts with the letter M will be followed by A, the very first ones. It's going to be MA. Then we can say the next ones that will follow from there, of course, of the MA ones, it's going to be, of course, 1, 2, 3, 4, 5 positions. So let's say the first one is going to be MA, H, just following the alphabet H, S, T, right? That would be the first one. Now we can switch the position. It's going to be MA, say SHT, can say MAH, sometimes yeah, so this is going to be MAHST, right? And then it's going to be MA, after H is going to be S, ne? Then we can say SHT, and then we can say MASTH. And then this one is going to be MAT, HS, is that it? Let me see. So this one's going to be MAH, MAS, but why H warming as P in the end? Because I see H is repeating here. 1, 2, 3, 4. Oh, let me do it again. You see, sometimes, guys, this thing can be tedious. Unfortunately, the mechanistic approach sucks, but what can you do? So this is going to be MA. Now we can switch the positions and say MAH and then say TS. Maybe let's do that first, because what will switch is going to be those last two. And then we can have MA. Now H is done because we cannot put H there. We can say this is going to be MA. The next one is going to be S. MAS. Then we can say SHT. Then it's going to be MASTH, right? Those last ones are just switching. And then the next one is going to be MAT, say HS, and then this one is going to be, it's going to be MATSH, right? Yeah. So as we can see here, these are the first few words that will start with the letter M after this 48. So these ones are what? 1, 2, 3, 4, 5. So from 48, we just add 5. So that's very crazy. So we can say, well, we can say just words that start with M alphabetically. Oh. We can say then words that start, come on, way that start with M alphabetically. So we can list all of those guys. It's gonna be M-A, H-S-T, M-A, H-T-S. This is gonna be M-A-S. H-T is gonna be M-A-S-T-H. And then it becomes M-A-S-T-H-S. I'm don't will indeed balap. This is gonna be M-A-T, sorry. H-S, and then it's gonna be M-A-T-S-H. Now there's many others, of course, that wait. The letters that start with the letter M should also be 24, are they not? Yeah. Khona into endingayifumani ke ngoku. 1, 2, 3, 4, 5, 6. Oh yeah, others are gonna be MS. Then the others are gonna be MH. Others, okay, cool. So, but these ones that start with MA, these are the ones. These are the first ones. So as we can see, this is number 5. So we can say, therefore, maths is in position 48 plus 5, which is equal to 53. Right. As you can see, guys, this is crazy. It's one of those nasty questions. Yes, we can use our techniques to get certain things right. Again, someone may have a better approach, but you know, when I get stuck with these fancy ways of doing things that are perhaps more concise, I don't shy away from the mechanistic approaches. As long as it gets me to the answer, I am happy. But if it doesn't, well, I can go and cry in a corner somewhere. Great stuff. So I hope, guys, you can see some questions can be very silly, but some people may have the smartest of ways to get things done. For me, as long as what you do works and you can do it properly, do it. Yes, consider time as well. Now let's get to this one. Now, folks, these questions are very nice and very interesting. These very 3, I need you guys to consider these questions for 1.3 in your paper 1. These questions can come in 1.3 in paper 1. So I need you guys to really think about these ones for that purpose. 1.3, 1.4, but that very last question on question 1 in maths paper 1 can be something like this. What would you do? So let's get to this question 24. Now question 24 says we simplify this thing. Now remember, if you put this on a calculator, it's going to say math error, because 2023 factorial is a very big number. It's like evaluating infinite. So automatically, even if you put it down on your calculator and say 2023 factorial, yeah, you will just see that it will just say math error. The reason is because that's evaluating infinity, and we don't have a value for infinity, okay? So you can't use a calculator here. So you're already screwed, if not really badly battered, if you try to use a calculator. It's not going to help. So basically, it's the understanding of the factorial notation. So I like these questions. After all has been said and done, we've suffered through all of these questions using factorials where possible. So what can we do for questions like this? Well, we will take it as it comes. 2023 factorial plus 2022 factorial divided by 2024 factorial. You know, my students were able to handle this nice and easy. Now, if you look at this, 2023 and 2022 factorials, there's a common factor there. Because 2023, we know that it's 2023 times 2022 factorial. 2023 factorial can be broken down to 2023 times 2022 factorial. Do you remember above when we had 3 factorial times 5? No. When we had 3 factorial times 4, we said that this could easily be 4 times 3 factorial. And if this is the case, this is as good as 4 factorial, right? Exactly the same thing here. So this is what you do, plus 2022 factorial. Can you see you've already uncovered the highest common factor there? Divided by 2024 factorial. Now, 2024 factorial is going to be a bit naughty for us at this stage. So at first, you just want to deal with things systematically. So just leave it for now. Don't rush anything. And then we get there, we will see, or perhaps we can actually break it. We can say this is basically 2024 times 2023 factorial, right? Right, but I'm feeling like, nah, man, leave it. Leave it alone. Let's just leave the 2024. I don't think it's going to work in our favor. No, it's not. So we're going to leave it as 2024 factorial, okay? We take out the highest common factor. This is 2022 factorial into 2023 plus 1, all divided by 2024 factorial. We go on. This is going to be 2022 factorial times 2024 divided by, maybe I should have gone ahead. This one becomes 2024 times 2023 factorial, isn't it? Same concept as what we just said here. So these ones take each other out. So we end up with 2022 factorial divided by 2020. Now remember 2023 is, okay, let's just leave it as such, 2023 factorial. Be patient. So 2022 factorial divided by 2023 is the same as 2023 times 2022 factorial. Yeah? Same idea as that, and these ones bow out, so we end up with 1 over 2023. This is the best we can get. Now, depending on how the answer is supposed to be given, there will be an instruction. So as you can see here, this is just playing with the factorials just to see if you understand how they work. And of course, this will demand no use of the calculator. So all the gymnastics, guys, factorizations, addition, subtraction, division, and what. Three-step approach, in essence, is at play. Okay, so that's how that question is sorted, guys. I hope you enjoyed it and you can handle it. So question 25. Question 25 says, given this situation, wow, this situation was a little scary when I first saw it, but yeah, sometimes you will see things for the first time and you need to know what to do. So can you see this is a factorial of a factorial? Yep, over 3 factorial is equal to a times b factorial. Okay, where a and b are positive integers. Can you see that? Now we're told b is as large as possible. So this is a very important statement. Now determine the value of a and b. This is typical of what you can come across in 1.3. This one is more closer. But you may have not seen what is a factorial of a factorial and a factorial. So basically this means you first deal with the inner bracket first, because you can't deal with this any other way. So you first deal with the inner bracket. What is that? So we know that we have ourselves here a situation where we've got 3 factorial is 27. No. Ah, man, come on, bruh. Yabona lento izondina manje. Yabona siyanhlanyisa. Ayingangiqheli kabi. Yini? Okay, guys, this first bracket on itself is suggesting that we're going to evaluate that inside the bracket. That's going to be 3 factorial, which is 6. Then we put that factorial outside, and then we put a factorial. So this is going to be divided by 3 factorial equals a times b factorial. Now we go on and say, okay, what is that? 6 factorial is 720. Then we put the outside factorial divided by 3 factorial. This is equal to a times b factorial. Now, if you look at this, you can see this is simultaneous equations, but looked at in a very strange way. We have done questions of this nature before. Now, 720 factorial is already infinity. So if you put that on the calculator, it's not going to work. So this means we need to change the right-hand side to look like the right. We need to change the left-hand side and make it look like the right-hand side, because that way we're going to win. Now, what is 7 factorial? 720 factorial is what? Now we need to break that up. And now we're told this should be as big as possible. So this is basically 720 times what? Basically 721, isn't it? No, 719, sorry. 720, 1 down. Just say 720 minus 1 is going to be 719 factorial, right? So that is the biggest we can have. That's what the statement is suggesting. So we know that we're using that same idea, that 3 factorial times 4 is as good as 4 factorial. Now we're breaking it back, saying 720 factorial is as good as 720 times 719 factorial. This is divided by 3 factorial is 6 equals a times b factorial. Now we know that 6 goes to 720 how many times? We can do that on the calculator. 720 divided by 6 is 120. So we know that this is 120 times 719 factorial equals a times b factorial. Can you see now? This is a whole number, this is a whole number. This is a factorial, this is a factorial. If that is the case, we know that we can conclude that A must be 120 and B should be 719. You can say therefore A plus B is going to be 120 plus 719. Okay, maybe let's say this is an implication rather, which also implies, then we can conclude. So that is the case, guys. So very nice and easy question, but very taxing at the same time. So this is 839. Very strange, nice simultaneous equation. Again, if you know how to deal with exponentials, this is the idea here. But again, in a very different sense. So don't cry when you see questions of this nature. They are typical of those 1.3 questions. You can find yourself dealing with them. So this is a very nice question, by the way. All right, let's get to the last question, 26. Now, question 26 says, determine the units digit of this sigma. Okay, now you're back to what looks like sequences and series. What are you gonna do? Well, we know that sigma, starting from I equals 1 to I equals 2023, of this general term I factorial squared. Can you see? It's very interesting. So this is the same as we put 1 factorial is 1 squared is 1 plus, then we put a 2 there, 2 factorial is just 2 squared is 4 plus, we put a 3 there, it's gonna be 3 factorial is 6 squared is 36 plus put a 4 in there, 4 factorial is 24 squared is gonna be 576 né? Plus, of course guys, you would want to do 3 terms because this seems easy, but the problem is that if you look at those first 3 terms, of course I'm doing this with the knowledge that I've done it before, but these first 3 terms don't form any of the sequences you know. Although at first we thought we'd probably be dealing with an arithmetic, which is much easier to work with the sum sometimes. But this kind of didn't fit any description. It's not an arithmetic, it's not a geometric, it's not a quadratic. And those are the ones in metric you work with. The moment it doesn't fit, then you keep going. It means there is some magic somewhere. Now, we will put, by the way, that was a 4. Then we put a 5, okay? So when we put a 5, it's going to be 5 factorial, which is, come on, man, 5 factorial. That is 120. 120 squared gives us basically 14400. Remember, this is when we square whatever we find. Now, folks, you can appreciate that what is going to happen here. As we get ahead of these things, the more we square those numbers, the zeros will just keep on increasing. Meaning, the digits of any of the other numbers up until 2023, there will be just more zeros at the end. Do you see? So this is where the secret is on this question. Now, what do you understand by units digits? Let's say you've got 2023. What is the units digit in this number? The units digit is the 3. In 2023, this is the units. Remember, we classify numbers as units, tens, hundreds, and thousands. Yes, so basically we're saying in this sum, what is this value there? The very last value. Now, as we can see, guys, from this we can say, therefore, the units digit here is going to be equal to, now we take all the units and add them together. So the units, remember, there's going to be zeros all the way until 2023. So we don't care. It's going to be 0, 0, 0, 0 plus 0 plus 0 up until we take 6. By the way, that 0 is going to be in and many other zeros somewhere. Then it's going to be that 6 and that 6 and that 4 and that 1, because those are the units. So whenever we add, remember, if you've got 516 plus 27, for example, there's a 0 there. So 6 plus 7, you add like that. Then you add those. So you see the units are going to add together. That's the same idea here. There's going to be more zeros every time we keep going. You can check again. Say that is, say, perhaps 50 factorial. Let's say that was 50 factorial. We get, 3,04 somethings, and then times 10 to the 64. Once we see that times 10 to the 64, it means there's going to be as many zeros. Okay, those 64 zeros there. So as you see, the zeros will just keep getting bigger and bigger and bigger and better. So it's all going to be zeros plus, so we just take those units that we can see. It's going to be 6 plus 6 plus 4 plus 1. Now that gives us 17, right? We transpose the 1. So we will end up with 7. So that's going to be 7, because out of 17 that we get from these, what can I say? Therefore, the unit digit is going to be equal to, we are going to add these, the ones I highlighted. So since the others are zeros, we don't care. This is going to give us 17, because this is 12 plus 5, which is 17. Then we only write the units, and then the other one was going to carry over to the next tens digit. So basically this is it, guys. So this is one of those tricky questions which are very likely to just amount to, say, 3 marks or 2 marks. And it's going to be there in 1.3, and you'll feel like you're being punked. But if you don't understand even the question, of course, you are already out of the game. So, of course, guys, we overthought this with my students, but again, it takes overthinking to become more finessed in what you do. All right, guys, so I hope you enjoyed the video. Give it a thumbs up. You can share it with your friends if you wish. As I said, I'm going to try to make my memo here available in the description, but I'm going to try to write nicely and neatly some things, and hopefully within 2 or 3 days of posting this video, it should be available for download. And yeah, if of course you want, can talk to these folks, the owners of this thing, and they can guide you in whether what I show here, or perhaps what you think, if it is different from mine, is it correct or not? Because here we are just building your confidence in the subject rather than to necessarily, solve problems. Because remember, problems are going to come in different variations, different techniques may need to be applied. But remember, every time the question is a bit more technical, it means more logic is needed to what? More logic needs to be applied, but that should be in combination with the basic ways of doing things. As I have shown here, the technique of just placing things on the grid and then thinking of options is the best way to go about business here. Otherwise, it hurts a lot. But you can see, once you get comfortable, certain things you don't even need to place on the grid. You just look at what you have, you look at the quality of the question, you just give the answers, and you are home free. Anyway, folks, I hope you have enjoyed the video and you have learned something, and that you will be able to do whatever you can to get your marks, be it a finessed type of technique or a mechanistic technique, like is the case for this question 23, you know. And others, as you can see, of course, you need to apply your math skills and your newly acquired understanding of factorials and what you can do when you multiply them. How do you break them down into smaller chunks that can be user-friendly? Of course, remember in maths, we always try to undo the situation. So try to make it align nicely so that you can undo whatever situation you need. All right, guys. Goodbye. I'll see you next time.